This video series, I'll be teaching you about functional programming in Python. Whether you're new to functional programming or familiar with it from other languages like Clojure, Racket, Haskell, or Scala, I want this course to be useful to you. For those of you new to functional programming, I'll cover the following: what functional programming is, what a pure function is and why it's a meaningful distinction, and why functional programming is desirable. Then I'll cover the practicalities of doing functional programming in Python, like basic techniques for functional programming in the core Python language, when it's appropriate to use, and most importantly, the libraries in the ecosystem that can help you. Specifically, I'll be covering these libraries: Toolz, which is a general-purpose utility library for functional programming; Pyrsistent, which provides high-performance immutable data structures; Hypothesis, which gives us property-based or generative testing; and Effect, which gives us a way to use side effects in pure functions. Throughout the course, we'll have a running example that we use to apply all the techniques and libraries that we learn about. We'll be developing a text adventure game that allows us to move around in a simulated world and interact with objects. Throughout the course, we'll implement some core simulation code, a text-based user interface, a storage backend, and a web application to give it a point-and-click interface. Along the way, we'll also do a lot of unit testing to make sure our code works reliably. In this course, I'll assume that you're an intermediate Python developer and that you have basic knowledge of development tools. You should be familiar with how to write functions, classes, and methods, and how to use and define decorators in Python. It also helps if you're familiar with some unit testing tools for Python. Thanks for showing interest by watching this introduction. Enjoy the rest of the series. Throughout this course, I'll be showing you examples that I encourage you to follow and run on your own computer. To do this, we'll need a development environment. I'm mostly going to assume you know how to use the basic Python development tools, but in case you don't, I strongly recommend this site, pythonguide.org. It covers installing Python on all the major platforms, as well as a number of attendant development tools. There are three I like to use to manage libraries: pip, virtualenv, and virtualenv wrapper. I'll run all of my examples with Python 2.7, but I'll try to write Python 3 compatible code. So the first thing I'll do is set up a virtual environment. I'll also install some of the libraries that I'm going to cover in this course. There may be others that I'll show you later, but this should get us started. It installed them. Let's just make sure our environment is set up correctly. That's everything we need. Throughout the course, I'll be writing most of the code on screen from scratch, so you can just follow along in the videos, but all the code I write is also available to download if you want to reference it or work on exercises yourself. When you want to run the code and you've set up a virtual environment like I've shown, make sure to use the work-on command to switch back to that environment so you can access all these dependencies we've installed. You can use deactivate to exit the virtual environment. These commands are only available if you're using the virtualenv wrapper tool. As you can see, the tools library is not available when I'm outside the virtualenv, and it becomes available after I've activated it. Remember, pythonguide.org is a great resource for learning how to set up your development environment. You should now be ready for the rest of the course. What is functional programming? Well, functional programming is programming with functions. That sounds a little bit silly, but there's a distinction between functions, as they're often called in imperative programming languages, and functions as used in the phrase functional programming. One way to think of it is that FP just emphasizes functions more than the many other programming concepts that we use, like classes, control flow primitives, and mutable data structures. It turns out that functions by themselves can give us a lot of the same power as those other things. But also, more specifically, functional programming is about programming with functions in the original sense, where the word function comes from mathematics. Here's a definition: a relation between a set of inputs and a set of permissible outputs with the property that each input is related to exactly one output. Let's break this down and map it to concepts we know about. The set of inputs are the values that we can pass as a parameter. This doesn't refer to sets in the data structure sense, but rather the set of things we're allowed to pass. The set of outputs are the return values we can get out of the function. And each input is related to exactly one output. This means that for any specific input, we always get the same result. For example, if we pass 7 to a function and we get back 10, we'll always get back 10 when we pass 7, no matter what the context we're calling it in. This is pretty different from functions in imperative programming languages. There are two big differences. One is the bit about always getting the same result for the same input. And that ties into another implied difference, which is that there's no room for side effects. What is a side effect? It's some behavior that a function or procedure can have that causes an observable change, other than just returning a value. Side effects are basically ways to break free of the restriction of only having input and output in functions. Functions that don't have side effects are called pure functions, only because the definition of function changed over time since it was originally used in mathematics. Programming with pure functions is called purely functional programming. So let me show you some examples to demonstrate. So here's a function. Can you tell if it's a pure function? And here's another. The first one is a pure mathematical function, and the second one has a side effect. I'll demonstrate. So we pass in the list containing 1, and we get back a list containing 1 and 2, and L hasn't changed. But if we call the second function with the same input, we get the same result, but L has changed. This is an observable side effect. When a lot of code is written with these kinds of side effects, it can make it harder to maintain and debug. Of course, we need side effects to do most useful things. We can't read input interactively from the user or display anything to the screen or communicate over networks without side effects. However, the vast majority of side effects used in imperative code are unnecessary. There's a pretty clear boundary between when a side effect is strictly necessary and when it's not. There are ways to write purely functional software that does things like network I/O and displaying things and even mutating data structures, and I'll describe those eventually, but you should know that there's a middle ground. Most code written in functional programming languages like Clojure, OCaml, and Racket is mostly functional. They still have commands that read from input devices or send network messages in a way that has side effects. That said, you still gain a lot of power from doing it most of the time, and this is what we'll be doing with Python. There are some programming languages, though, that have interesting ways to express all code as pure functions, even stuff that does network I/O or displaying to the screen and so on. And we can apply some of those ideas to Python as well, and I will get to that later in the course. We're going to start with pretty light functional programming. I'll describe some things you can start using right away, and then gradually teach you more and more about functional programming, so more and more of your functions are really functions in the mathematical sense. Eventually, we'll get to the point where we're even using some ideas from Haskell in our Python code. You don't have to go that far, though. I'm going to cover the whole gamut, and you can use as much of it as you're comfortable with in your own projects. Many people say that learning functional programming will change the way you think and lead to writing better software. I definitely think that's true, but I like having more specific reasons, and I want to demonstrate some for you. Programming is a pretty wishy-washy thing, as much as some people say it's strictly logical. At least when it comes to software development projects, especially on teams. The success of software projects is pretty significantly affected by the happiness of developers working on it, and I suspect this is often more important than the specific technology choices made, up to a point. So in that sense, working with a paradigm that is beautiful and fun and cool and exciting can lead to better software. Here's a link to an interesting article about a psychological study that some computer scientists did about how happiness affects problem-solving skills. I recommend reading it. But there are also pretty strong concrete reasons to use functional programming other than just how pretty it is. I'm going to go over some arguments that I consider compelling in favor of FP. I'll break these arguments down into a few different sections: expressiveness, reasoning, testing, and performance. While the main technical requirement of functional programming is just writing pure functions and avoiding side effects, there's a whole other level to it. Since the focus is on functions instead of built-in constructs like loops, variable assignment, and classes, it becomes easier and more natural to write our own abstractions. This allows us to solve problems not just concisely, but with fewer concepts at once. That's some highfalutin talk, so here's a really trivial example. Now, it's a testament to the Python community that this has actually become kind of unidiomatic over recent years. Modern Python programmers would probably use a list comprehension, which is a wonderful functional programming tool. But this imperative kind of for loop is still really common in Python, especially in more complex, longer functions. You'll walk over a list of inputs, calculate something for each element in that list, and accumulate the results in some output list. Now, an idiomatic FP solution would look like this. While this second form may be unfamiliar, it's much clearer than the first form once you know the concepts, mostly because there are fewer concepts involved. If you look at the imperative version, you'll see that it has a for loop, it has two local mutable variables, I and x, and it initializes and mutates a result list. If you compare that to the number of concepts in the second one, all you have is the concept of mapping over lists and function composition. Not only is the second form shorter, it has less room for surprises because of its simplicity. It takes advantage of what we call higher order functions, which are functions that use other functions as first-class objects by either accepting them as arguments or returning them as results. You can think of a higher order function as kind of a template which you can pass some other function in to plug the holes. Map is kind of a template function like that. It uses the passed in function to perform a calculation on each element of the list. Other examples are the filter function, the sort function, and all function decorators, which not only take functions as arguments but also return new functions. So on to the next benefit, reasoning. The functional programming community puts a lot of stock in mathematical rigor. There's a great focus on correctness, which is appealing to me after working so long with more ad hoc programming methods. There's also a focus on being able to reason about our code. If you've heard people using that word but don't know exactly what it means in the context of code, I'll explain. Reasonability is kind of like readability, but it involves more than just reading code. It's about being able to think about code. Imperative code is harder to reason about since things can change at any time. Functional code is easier to reason about for a couple of reasons. First, it allows you to assume things about your code which are often impossible with imperative programming. Second, the expressiveness you get from using functional abstractions allows you to write simpler code. These 2 points kind of synergize to make reasoning easier. Your functions are more concise and involve fewer concepts, which allows you to fit more of them in your head. And since they don't have side effects, you don't have to worry about what the dependent functions do or the various states your program could be in. For example, when you follow a functional paradigm and you see a function like this, you don't have to worry about what f1 and f2 are doing. You can call them interactively to see what kind of values they return. So as we see, calling f1 with the list of 1 and 2 returned a list of 2 and 3. And calling f2 with the string foobar returned that same string foobar but wrapped in a list of only one element. When your code is functional, you can assume they'll always return those values for the same inputs. This is what we call equational reasoning, meaning you can kind of mentally replace any call to a function with that call's return value, and your assumptions will still hold. So because we know what f1 and f2 are going to return, we know that our foo function, when given the list of 1 and 2, and the string foobar, will return the list 2, 3, and foobar. As you see, the output included OK, so our assertion passed. Now you don't need to worry about those functions mutating x or y, or messing with some global mutable state. Of course, this is all on the honor system, since Python doesn't have any way for us to prevent these functions from doing those things, but if you apply these ideas consistently, you can still gain a very real benefit to reasonability. So beyond letting us reason about our code better and express our functions more concisely, how else does it help? One of the greatest benefits I feel like I've gained from doing functional programming is in how easy it is to test. The majority of large Python apps I've seen use a lot of mocking. In my experience, it can easily become kind of a nightmare. Our tests end up specifying deeply nested mocks where a mock returns a mock returns a mock. And on top of that, they're often specified in ad hoc one-off ways, and it leads to tests being overly coupled to implementation concerns, even though the goal of mocking is to avoid that coupling. With functional programming, the necessity of mocks, especially deeply nested ones, can be greatly reduced, if not eliminated. Pure functions can't have side effects, so the only observable behaviors are tested by calling a function with some arguments and checking its result. There's no need to track complex side effects through stateful mocks, since we've eliminated those side effects. Of course, there will always be side effects, but by being cognizant of where we use them and restricting how deeply they infect our code bases, we can make a large part of our code much more easily testable. Perhaps more important than the lack of side effects, though, is that writing functional code leads us to more modular code. Instead of putting some method on a class that has some data dependencies that are irrelevant to that method, you write a function that only accepts the arguments that it strictly needs. Testing that function then becomes trivial. To demonstrate, how many times have you seen a domain model like this? We have a user class that accepts some database store, an ID, the name of the user, and the organization that that user belongs to, and it assigns those to attributes on self. It has some methods for interacting with the database, for loading related objects, and then some utility method for getting the email address of the user that combines the name and the organization. To invoke that method, we need to instantiate a user with a store, an ID, a name, and an organization, even though that method only actually acts on name and organization. Now, some people will say that this is a poorly designed model object, and I would agree. The point is that this is an easy mistake to make with object-oriented programming. With functional programming, it's much more natural to do something like this. When we want to test get email address, we no longer need to figure out how to get a store and an ID. We just call it with the data it needs. Not only that, it means that our get email address function is reusable in more situations in our application code. This is how writing small functions leads to modularity and testability. In my experience, this is one of the biggest benefits of functional programming in Python. We don't have a powerful ahead-of-time type system to verify the correctness of our code, so we have to put a lot of effort into our unit tests. We should try to make those unit tests as easy as possible to write, and we do that by making our code as testable as possible. And FP code is the easiest code to test. Finally, there's one other benefit to functional programming, and that's performance. Purely functional code is easy to run concurrently. The fewer side effects you have, such as shared data mutation, the easier it is to run on multiple CPU cores. The reason that multi-threaded code is normally difficult is that we have to spend so much effort on protecting shared data and coordinating around side effects with things like locks. Of course, Python has a rocky relationship with multi-core programming because of the global interpreter lock. But it can still be done in a few ways, and it's a lot easier when you're using pure functions. The two notable ways to take advantage of this are multiprocessing and PyPy's software transactional memory. Multiprocessing is widely available now. This gives you an API for running functions in other processes and passing the results back to the main process. And as for software transactional memory, as of this writing, it's a feature only available on the PyPy interpreter, but that's honestly what anyone who's concerned about high performance should be using anyway. STM is a mostly transparent system that kicks in anytime you're using the Python threading APIs. When your code is purely functional, it will be automatically and properly parallelized onto multiple cores. This is different from the normal threading APIs on CPython, which do use multiple threads but don't allow Python code to execute simultaneously because of the global interpreter lock. If you have side effects that conflict with one another, the STM system automatically reverts the transactions and reruns them until they can complete without contention. Now, this point about performance is probably one of the biggest reasons that functional programming has recently gained so much traction in the wider industry. Since CPUs aren't getting faster, but they are getting more parallel, we need a programming paradigm that parallelizes easily, and functional programming is it. In case you need any more reasons to do functional programming, and you find argument from authority to be persuasive, I like to use John Carmack for this purpose. He was the lead programmer on the video games Quake and Doom, and is also literally a rocket scientist. He's easily one of the best programmers I've ever met, and he advocates functional programming. He says, programming in a functional style makes the state presented to your code explicit, which makes it much easier to reason about. And if I had to write software that my life depended on, I would seriously consider using Haskell. Other, more corporate interests have also been bringing functional programming closer to the mainstream. Microsoft Research has released F#, which has a quite strong approach to functional programming. Apple also released the Swift programming language this year, which has fairly good functional programming support, especially in its immutable data structures. And Java is getting there. The recent Java 8 release finally included lambdas and closures. Those are some reasons why I think functional programming is worth using. If you're interested in more material rationalizing the use of functional programming, John Hughes wrote a paper in 1989 called Why Functional Programming Matters. It's maintained its relevance to this day, and I recommend checking it out.
This lesson is about using Python's built-in functionality to do functional programming. Python provides a couple of important features that allow us to write functional code. The first is that functions are first-class values, meaning they can be passed around like any other value and returned and so on. The second is that these first-class functions can capture their environment. That is, functions have closures. Closures are basically a set of variables that get carried along with a function when we pass it around. Usually a variable in a function disappears when that function returns, but if an inner function references that variable, it'll be attached to the inner function and travel along with it. This is sometimes referred to as capturing the environment. This facility is used quite a bit in Python code, and we'll be seeing a lot of examples of it. First-class functions with closures are really necessary to have meaningful functional abstractions, and so it's great that we have them in Python. However, at the same time, Python misses a lot of the features that are commonly useful in functional programming. First, it doesn't have a strong library of pure functions. Most of the standard library is very object-oriented and imperative. It doesn't have efficient immutable data structures, and it doesn't have cheap recursion. The first two of these things can be remedied with third-party libraries, and there are even tricks for dealing with recursion in efficient ways in Python. But in this lesson, I'm going to focus on what Python itself provides us for functional programming. It'll also serve as an introduction to some common concepts of functional programming in general. Other lessons will cover what we can do with a larger ecosystem by using third-party libraries.
I want to talk about higher order functions, but I'm going to take a detour with recursion first. Imagine you're a functional programmer from ancient history. Your programming language only has functions, plus some basic data types, and you want to repeat some code for every element in a list. Well, since loops haven't been invented yet, you're going to have to figure out a way to do this using only functions. Let's say we want to add up all the numbers in a list. How about this? Here we rerun the code in the mySum function by calling it at the end of that same function. Since the mySum function is calling itself, this is called recursion. This is about as simple an example as we can get, but it has a couple of concepts that we can see in a lot of different cases. The first thing we do in this function is check if the argument is an empty list. We return 0 to represent the sum of no elements. This is what is often referred to as a base case. It's the case of our function where we don't need to do any further recursion. When traversing data structures like lists or trees, this is almost always represented by an empty data structure. It's useful to think of this as reaching the end of the list. The else branch runs when we have a list with at least one element. Here is where we do our recursion. We add the first element of the list to the result of recursively calling mySum on the remainder of the list. This is a very common pattern. You do some work on the current element of a data structure and then make the recursive call with the rest of the data structure. Here's another example. Let's add 1 to each number in a list, producing a new list. Here our base case returns an empty list since there are no elements to increment. But when we actually have some data to work on in the else branch, we add 1 to the first element of the list and then make the recursive call with the remainder of the numbers. We prepend the result of the addition to the front of the list with the plus operator. Note the similarities with the mySum function. Our base case is when an empty list is passed. In mySum, the result of 0 represents the sum of the elements of the empty list, and in add1all, the result is another empty list since there are no elements to add 1 to. Then in the recursive case, we do some work on the current or first element, and then make the recursive call on the remainder of the elements, and combine them together to build up to our result. I think these examples so far are good for demonstrating the core ideas of recursion, but they're not really good Python code. For one, we're just re-implementing built-in functions like sum, or defining a new recursive function where a simple list comprehension could have done fine. On top of that, these recursive formulations aren't good from a performance perspective either. All the list concatenation is very inefficient, and big enough inputs would actually cause our program to crash with a Stack Overflow because of all the recursive calls we'd have to make. However, there are still situations in which recursion is the most straightforward solution to a problem. Let's take a look at an example that's a lot more realistic in Python code. First, let's set up a scenario. Here we have a domain model of groups of people. Groups can contain members, but they can also contain other groups. Perhaps we're modeling a company's organization or an access control mechanism for a content management website. What if we want to get all the members of a group, including the members in that group's subgroups? The most natural and idiomatic way to write this, even in Python, would be with recursion. So when we make this call, we should expect to see Sam, Jesse, Reese, and Taylor. And we do. Great. This function goes through all the subgroups of a group and accumulates their people into a big list. It then concatenates the group's direct members to that list of people in the subgroups and returns that. This function looks pretty different from the previous examples. For one, it may not be obvious where the base case is. There's no explicit if statement checking for a trivial input. However, any recursive function that completes must have a base case. So where is it? Well, the base case is what happens for an input that doesn't require any recursion, and it still exists here. It's when a group with no subgroups is passed. In that case, the body of the for loop will never execute, thus no recursion will happen. The other part, where we combine the current element with the remaining elements, is pretty similar. The combination operation is when we concatenate the group's direct members with all the subgroup's members, which we've calculated recursively. That about covers it for the basics of recursion. Next, we'll explore some more patterns with higher order functions. I've mentioned general patterns in these recursive cases a few times now. Being good functional programmers will want to create abstractions so we don't have to type out the same pattern over and over again. But the ancient functional programmer doesn't have classes, so we'll have to figure out a way to create these abstractions using only functions. Let's take a look at our add1all function again. Let's say a few years have passed, and our ancient programmer now lives in a land with classes and inheritance, as well as first-class functions and closures. Yesterday I wrote the add1all function, but today my boss told me I need to write a function that increments each element in a list by 2 instead of by 1. Well, I could just call add1all twice, but it turns out that's too slow on my 1970s hardware. I'm going to need to write a new function. All done. That was a hard day's work. Of course, we should notice a pattern here. This add2all function looks almost exactly like add1all, but instead of adding 1, it's adding 2. It would be great to have an abstraction to perform some arbitrary computation on each element in the list, and not have to worry about all the bookkeeping around that. An object-oriented programmer might write a class to create this abstraction. This may be typical for old-school Java programmers, but it's pretty unwieldy. So what about using those first-class functions? There we go. Not only was it easy to create that map function, it's super easy to use. This is the usual procedure for abstracting common functionality with functional programming. And you'll use the same method whether you're creating some little control flow tool or writing domain-specific application functionality. What about our sum function? It doesn't look like it's the same kind of recursion algorithm as our add1all and add2all functions. Those ones produced a list where each element was replaced or mapped to something else. But sum only returns an integer, not a list. Let's get another example of a similar shape so we can see what kind of generalization we can make from it. Here's a function that calculates the length of a list recursively. We can see that this has a very similar shape. Both mySum and length compute a value based on the current element, like map does, and then numerically adds that value to the result of a recursive call on the rest of the list. We can abstract that like this. That let us formulate our sum and length functions a little bit nicer, but it's a pretty specific abstraction. It only deals with cases where we're adding up numbers based on a list. That's not very powerful. Let's explore some more patterns of recursion to try to figure out what else we can generalize. Say we want to find the biggest number in a list. This is a new pattern in our recursive functions. Here we've added a parameter called currentBiggest, which is used to keep track of some data while we're recursing through the list. In every step of the recursion, we check if the current number is bigger than the current biggest, and if so, treat the current number as the new current biggest by passing it to the next recursive call. This also changes our recursive case in a subtle way. We're no longer combining some result of processing the current element with the result of a recursive call. We're only making a recursive call. This is just another style of recursion where instead of accumulating the result in the return value of the function, we accumulate it in a parameter to the next case, and then return the fully calculated result in the base case. Note that our base case returns the value passed in as currentBiggest instead of something like 0. Here's a generalized higher order function that can handle both the biggest case as well as mySum and length. MyReduce takes a function to call, a list, and an initial accumulator value. The function is called with an element from the list and an accumulator, and the return value of f is used as the next accumulator. The way this accumulator value is passed from call to call, allowing each one to modify it, lets us do a lot of things. As you can see, this function is quite powerful. It lets us specify all of those different recursive algorithms in a very concise way. It even lets us write map and filter in a much nicer way. There's our new formulation of map and the add1all function. And here's a filter function and an evens function based on that returns all the even numbers in a list. Notice how we can use the accumulator value in a couple of different ways. In the biggest, length, and mySum functions, we reduced the two arguments we received to a number, which represents a partially complete operation. In myMap and myFilter, however, we're using it to accumulate into a modified list. As I said earlier, recursion is not very well optimized in Python and runs into problems with very large inputs. But it turns out we can take advantage of these higher order functions we've written to avoid those problems. Since they hide the recursion, we can rewrite them in iterative ways. This version of MyReduce has the same interface as our older one, but it doesn't use recursion. And all of the existing functions that use it will continue to work. This is an example of how using high abstractions in our code can allow us to optimize things later without having to refactor other parts of our code. The higher our abstractions, the more opportunity we have to do this. Higher order functions can be used to abstract away more than just recursion. They allow us to generalize any kind of pattern we find in our code by factoring out the commonly recurring parts into another function. These functions can parameterize some other computation that we want to provide on a case-by-case basis. To start from the basics, when we write functions that take parameters, we generalize a pattern and parameterize a value. For example, if we have a function add5 that takes x and adds 5, we're generalizing the addition of 5 to any input. Higher order functions are the same kind of idea, but instead of generalizing around a simple value, we generalize around an arbitrary computation. Let's start with an easy example, tracing the flow of our programs. Say we have this pattern. At the beginning of each function, we're printing a message with the name of the argument, and at the end of each function, we print a message about the result. This is a lot of typing for every function we want to trace. We can see that the code looks very similar. First, we print the name of the function and its argument, then we do the calculation, then we print a message with the result, and then we return the result. We can refactor this code using a higher order function. And now our functions can be made much more clear. It turns out Python has a feature for applying higher order functions at the site that functions are defined. This is with the built-in decorator syntax using the @ symbol. We can write a decorator for our trace function like this. Here we take advantage of the special name attribute of Python functions to determine the name of the function. And now we can change our code to use Python's built-in decorator syntax to use this decorator. Much better. That's about all I'll say about higher order functions and decorators for now, but we'll see a lot more examples in our functional code. Python has great built-in data structures, but in general they're very geared toward in-place mutation. But the functional style calls for immutable data structures, where we want to return new versions of a data structure when we perform operations on it, so that we can reason about it more easily. At some point, pretty much all big Python programs end up with bugs caused by spooky action at a distance due to data structure mutation. Say you have some code like this. And most of the time, you end up calling this function with a list literal. But one day, someone comes along and adds a call like this. Now you might have a bug that's very hard to track down, because getList might be holding onto a reference to the list that it returns, and using it for some other reason later. The call to add item mutates the list in place, which affects all the code that holds a reference to that list. This simple example applies to all mutable objects in a complex Python app, and they're not very hard to let them slip in, unless you know what you're looking for. So instead of mutating the list in place, we'll rewrite that function to return a new one. Now our function's safe no matter what other code may do with the list that's passed in. This idea also applies to custom classes in our Python programs. Say we have a two-dimensional point class. The translate method modifies the data structure in place. Again, this is something we want to avoid with functional programming, so we could instead write it something like this. Now our translate method returns a new point object, avoiding any possible bugs caused by the mutation. Sometimes you've got to deal with data structures that don't have any built-in non-mutating operations. For example, while the list type has a purely functional plus operator, there's no method for adding items to a dictionary without mutating it. So how can we merge the dictionaries A and B? Dictionaries happen to have a copy method. So even though we end up mutating the dictionary, if we create a copy of it first, we maintain purity. But what about instances of classes? Sometimes we can avoid the need to explicitly copy and mutate our instances, but not always. Our point class, for example, worked fine because all of its data was parameterized in the constructor, so we could just create a new one. But if that's not the case, you may need to use the copy module to explicitly create a copy of an object before mutating it. That about covers it for dealing with built-in data types and objects in a functional way. With the help of third-party libraries, we can get much more convenient and performant functional data types, but these techniques will get you pretty far in standard Python. In this lesson, I'll be introducing the Pyrsistent library, which provides a collection of efficient immutable data structures. The ease of use and efficiency of Python's built-in data structures has certainly contributed to its general success, but they're very geared toward mutation. They aren't very fast or easy to use when you want to use them in a purely functional way. Usually we just end up copying the entire contents of some data structure and mutating the result when we want to avoid side effects. For example, if we have a list of a few numbers and we want to replace the last element without mutating the original, we have to do something like this. This is usually fine, but it can take a significant amount of time if the list is large enough. Not to mention it doubles the necessary memory. Pyrsistent offers a number of data types that allow modification which return new values instead of mutating the old ones, while still maintaining high performance even when the structures are large. Before I get into how that works, I'm going to show you how to use these types. Pyrsistent has a whole lot of features, but the most commonly used ones are vectors, maps, and sets. I'll also cover the p-class functionality that it provides for writing custom immutable classes. P-vectors are what you want to use to replace Python lists most of the time. They represent a one-dimensional array of elements that you can index, append, or modify efficiently. We can convert a built-in list to a p-vector with the p-vector function. There's also the v function, which is a polyvariatic function that gathers all of its arguments into a p-vector. Looking up elements is exactly the same as any other sequence in Python. But when we do things like append, it doesn't mutate the original. We can't use Python's index assignment syntax since it's a statement instead of an expression, meaning it can't return a value. Instead, Pyrsistent provides a set method, which results in a new vector. Next up are p-maps, which are the immutable version of a dictionary. Like p-vectors, we can look up, add, or replace items quickly. We can convert a built-in dictionary to a p-map with the p-map function, and the m function returns a p-map based on the keyword arguments passed. Indexing is supported normally, and modification is again done with the set method. Finally, p-sets are the analog to Python sets. The API is very similar in this case. Again, there are two ways to construct a p-set. The p-set function, which takes an iterable, and s, which is polyvariatic. Here we use the pipe operator to produce the union of these two sets. And just like the built-in set interface, we have add and remove methods, but they return new versions. The p-vector, p-map, and p-set functions allow you to convert iterables into their respective data structures. But you can also convert nested data structures between persistent and built-in versions with the freeze and thaw functions. I personally find these very useful when converting to and from JSON data types. Here we create a nested structure of dictionaries, lists, and sets. Then we can freeze it, producing an immutable version. Then we can use the thaw function to convert the immutable version back into basic Python data types. The last feature of Pyrsistent I'll cover is p-class. It's a way to define our own classes whose instances should be immutable, while supporting convenient ways to update their values to get a new instance. To use p-class, subclass it and declare all of your attributes as fields. Here's a point class representing two-dimensional coordinates. We defined a translate method to use the set method, which is inherited from p-class. This takes keyword arguments specifying the new values of the fields. We can construct a point by passing a keyword argument for each field. And we can call our translate method. Of course, the original is unmodified. We can only set attributes that we've explicitly declared. And we're also prevented from directly mutating the instances. We can also convert these instances to plain dictionaries with the serialize method. P-classes have some other more advanced features like type checking and specifying default values for fields, but that's all I'll cover for now. If you're curious about how Pyrsistent stands up to the built-in data structures with respect to performance, we can explore that. In general, Pyrsistent is pretty much always faster than the built-in types if you're doing non-mutating modifications. Let's try doing some casual benchmarking just to get a feel for it. Running these functions with 0 shows us how much time it takes to append an item to an empty list. Here we see that the built-in list and the persistent vector are about the same. But as soon as we bump this up to one element, persistent vectors start winning out. The most notable thing, though, is that as the size of our input grows, adding an element to a persistent vector remains constant time, whereas adding an item to the built-in list takes more and more time since we need to copy the whole thing. But of course, if we're comparing immutable modifications with direct mutation, the latter pretty much always wins, but perhaps not by as much as you'd expect. Let's benchmark that. This benchmark tests how long it takes to cumulatively add 1,000,000 elements to a 1,000 element list. The persistent version takes a little more than twice the time, which in my opinion is fast enough that it's worth using these data structures by default in our code, and only switching to direct mutation when the performance is called for. Having the peace of mind of functional programming makes it worth it. Next up, we'll talk about how persistent works under the hood. Now let's talk about how persistent data structures work. I'm going to prime the idea with a very simple and well-known data structure, linked lists. These aren't used very much in imperative programming languages because they don't perform very well given what people want to do in those languages. But we can learn something about how persistent structures work through them. A linked list is a series of nodes with two references each, a reference to the data in the node and a reference to the next node. In Python, we can easily model these with nested tuples. Here's the linked list containing the numbers 1 through 3. We use none as a sentinel value to indicate the end of the list. Appending an element onto the end of this list is a rather inefficient operation. Since we can't mutate the list to replace the none at the end, we're going to have to create a new tuple representing the new tail of the list. Then we're going to have to replace the tuple containing the 3 with a new tuple wrapping our new tail. Then we're going to have to replace the tuple containing 2 with a new tuple wrapping that, and so on, until we get to the front of the list. We can generalize this procedure with a recursive function. Since we have to reallocate all of these objects, this is pretty slow. This is a big reason linked lists have kind of been shunned. However, some operations are fast. For linked lists, pushing an element onto the front is much faster than appending to the end. This is because we only have to create a new tuple containing the new element and the existing list. The performance properties of linked lists are usually pretty prohibitive in a language like Python, but this idea of sharing structure between immutable data structures has been developed a lot over the last decade or two, and there are much better alternatives. These advanced data structures are exactly what Pyrsistent provides for us. The core data structure used in Pyrsistent is called a persistent array mapped tree, or vector tree. This is a data structure that stores an array of elements in a tree structure. It does this by taking chunks of the array and distributing them into the leaves of the tree. The reason it's called persistent with an E doesn't have anything to do with the persistence in the sense of saving something to disk. Rather, it refers to the fact that when you change something in the structure, the original structure stays in place. This is really just kind of a nitpicky word for an immutable or functional data structure. The distinction is only that persistent data structures may actually involve mutation under the hood, but they don't expose it in their interface. Here we see a vector of 8 numbers. Each group of 2 elements in the array is broken up and stored in the leaves of the tree structure. The branches of the structure basically contain some bookkeeping data that allow us to find the elements we need. So in order to find, say, the last element of the array, we only need to walk through 3 steps. First the root, then the last intermediate branch, then the final leaf node containing the last chunk of the array. This is a lot better than linked lists, where we have to walk the entire structure to get to the last element. Just like pushing an item onto the front of a linked list is efficient, we can get fast updates to array-mapped trees by copying only the nodes that directly reference the values we want to change in the original tree. Here we see another vector of 8 numbers, and then a new vector that was produced by changing the 5th element to 99. The new version only consists of 3 new tree nodes, the root, 1 intermediary node, and a modified copy of the chunk of the array which contained the 5th element. This is the benefit we get from structure sharing. The time it takes to look up or modify elements in a tree like this is a function of the branching factor, which in this example is 2, and the number of elements, which is 8 here. These parameters aren't very good for modern computers, I'm just using them to demonstrate the idea. If we had a vector with 1,000,000 elements, looking up an element by index would require quite a number of traversals through the tree. If my math is correct, somewhere around 20 nodes. By increasing the branching factor to 32, which is actually what the persistent library uses, we only have to traverse 4 nodes to get to any element in that vector. This also means that to update any element in this element vector, we only have to copy 4 nodes. Much better than copying the whole thing. What this all comes down to is that we can treat indexing and modification of persistent vectors to be effectively constant time. This isn't technically accurate, but what it means is that we know it'll fit within some very small amount of time for any vector that we can fit into memory on our computers. It's the time it takes to dereference and compare a handful of pointers. There's a lot more I could cover on how persistent works, but it would take far too long. If you're interested in deep data structure arcana, I strongly recommend checking out Jean-Nicolas Lorange's excellent series of articles about Clojure's persistent data structures, which the Pyrsistent Python library is heavily based on. In this lesson, we'll cover Toolz, which is a general-purpose library of functional programming abstractions. It's billed as the functional standard library for Python, and I think it does quite a good job at that. There are three main areas of functionality that Toolz covers. The functools module has general functional abstractions, mostly higher-order functions. The itertools module has functions for working with iterables, including lists, tuples, iterators, etc. The dictools module has functions for working with dictionaries. The standard library has a couple of built-in modules that are along these same lines. They're called functools and itertools, but with an S. The modules from the Toolz library kind of correspond to the standard library modules. They basically provide the missing features of those built-in libraries with a much more functional bent. I'm only going to give you a taste of the things that Toolz covers since it's quite a big library, but don't worry, despite being large, it's quite simple and it doesn't have a lot of conceptual interdependencies, so it should be easy to use bits of it piecemeal. The tools.functools module is the smallest of the three parts of Toolz. The bits of it that I use most often are compose and curry, so I'll cover those now. One of the functions that's very common in functional programming is compose, which composes two functions together. It's mostly useful when it has a short syntax, like in Haskell, which uses the period operator. But even as a named function, it quite often comes in handy. So what does it mean to compose two functions? Well, I think it's useful to demonstrate this as an equation. So composing two functions f and g returns a new function. When you call this new function, the argument is first passed to g, then the result of that call is passed to f, and the resulting value is returned. Note in particular the order of the functions. They're called from right to left, which matches the way functions are applied normally. Usually in Python, we do this by defining ad hoc functions, like this. Instead of writing that compose function manually, we can use the compose function like this. Usually we only use compose when we need to pass a function to some other higher order function. It would be silly to write a call this way instead of just calling f and g directly. But say we need to pass a compose function to map. Using composition is tidier than having to write a lambda by hand in this case. Currying is another feature provided by Toolz. This is a famous Haskell feature. In fact, the name of Haskell is a reference to Haskell Curry, who invented currying. In the Haskell language, all functions only take one argument, but multi-argument functions are still possible by having a function return another function when it's called with each argument in turn. So for example, a plus function that takes two numbers is actually a function that takes one number and returns another function that takes the final number, which, when called, returns the result of adding the two numbers. It turns out that this can be very useful when doing functional programming, because we can pass around these intermediary functions. For example, with currying, we'd be able to add 1 to each number in a list very concisely with map. The Toolz library offers a very handy decorator for automatically enabling this kind of currying on a function. Now we can actually run our map example. The curry decorator works by analyzing the decorated function to find out how many arguments it takes, and then returning a partially applied function whenever fewer than the necessary number of arguments are passed. It's worth noting that there's also a built-in function for partial application in the functools module of the Python standard library. It's called partial. The difference is that this function isn't automatic like currying is. You have to explicitly create a partially applied function, instead of just doing it by calling the function with fewer than all of its arguments. The functools module also has a couple of other useful functions that I'll briefly mention. The identity function just returns what it's passed. It's handy when you need to pass some function that doesn't transform its argument to a higher order function. The memoize decorator permanently caches results based on arguments to the function, so multiple calls with the same arguments won't have to recalculate the result. Of course, it should only be used on pure functions. In this case, the x plus 3 is only run the first time we call foo, and in later calls, it just returns the cached result. There are several more functions, but I'll move on to itertools. Itertools has a bunch of useful functions for dealing with iterators and sequences. If you've ever had an iterator object and you want to deal with it kind of like an in-memory list, like this, if I want to get the third element of this iterator, I can't just index it. I'd have to do something like this. However, with Toolz, we can use some handy functions that they provide. For example, if we want to get the third element of an iterator, we can use the nth function. Likewise, there's a convenient last function that returns the last item of an iterator. It's very important to keep in mind that Python iterators are intrinsically impure because consuming them mutates their internal state. It's certainly possible to build useful pure functions using iterators, but you'll have to be careful since you can't use equational reasoning with them. Here we see that we can't call the last function on the same iterator twice, since it consumes the whole thing. Tools has many other useful functions. Here's a little whirlwind tour. The drop function returns an iterator of elements after skipping some. And the take function is kind of the opposite of drop. It returns only the first so many elements. Group by returns a dict containing groups of values determined by some key function. In this case, we're using the first function to group by the first letter in each string. Interpose takes an iterable and returns an iterator where the first argument is inserted between each element of the given iterable. This is basically a generalized version of the very handy string join method, which works with any type of element. Another useful feature for all of these functions is that they work equally well on iterators and concrete sequences. So for example, while we can't use the next built-in function on lists, we can use first on either sequences or iterators. That's all I'll cover on the itertools submodule, but there's plenty more. The dicttools module isn't quite as big as the itertools module, but it's quite useful. It basically provides a purely functional API for working with dictionaries. Say we have two dictionaries and we want to merge them. Usually we'd have to explicitly copy and modify them. Instead, we can use the merge function from dicttools. Likewise, we have assoc for adding a single item and dissoc for removing an item. Getin is another handy little function. It takes a list of keys and retrieves the element specified by those keys in a nested structure. This may not seem very useful at first, since you could also just write this. However, it really shines due to its optional third argument, which is a value to return if any of the keys in the list aren't found. This is otherwise very tedious to spell with Python's built-in features. It's similar to the dict.get method, but it handles the lack of a key on any lookup on the way to the final result. The tools.dicttools module kind of plays the same role as Pyrsistent's pmap data structure, but instead of defining its own efficient immutable data structure, it works by simply copying dictionaries under the hood. So it's not as efficient, but it's useful when dealing with Python code that may rely on mutable dictionaries. It lets us use functional operations on them in our own little space. The documentation at tools.readthedocs.org is very good. Not only does it cover the API and features that the package itself provides, it has quite a good introduction to functional programming with Python. I recommend checking it out. It's also worth familiarizing yourself with the built-in modules functools and itertools. The documentation can be found on the Python website or by using help in your Python interpreter. This lesson will briefly introduce Hypothesis, a quick check style testing library for Python. Hypothesis allows you to write tests by describing properties of your functions. To test these properties, it automatically generates inputs for your functions and checks your properties in terms of those inputs and the results. In order to generate those inputs, we need to tell Hypothesis the domain of valid inputs to our functions. To give a very simple, concrete example, here's a traditional unit test for a function that adds 2 to a number. With Hypothesis, we can write a test like this. We use the given decorator to specify the type of input we want, and then we just write a simple assertion using that input and our add2 function. When test_add2 is called, Hypothesis generates a bunch of random integers and calls our underlying unit test with each one. By default, it does this 200 times. As you can see, this unit test is a lot more concise since it frees us from the need to come up with our own specific test cases. Of course, we can use Hypothesis for things more complicated than just integers. Say we have a custom implementation of sum and we want to make sure it has the same behavior as the built-in sum function. For this, we'll need to generate a list of numbers. Here, we'll use a strategy which indicates that we need a list of integers. It turns out we have a bug in our mySum function, which we didn't catch in our handcrafted test case. We need to handle the case of an empty list, which we can do by passing 0 as the initial value to reduce. There, we fixed it. We're not limited to simple built-in types. By creating our own strategies, we can have Hypothesis generate instances of our own custom types. Let's say we have a class that models a herd of animals. We'd like a strategy that can create random herds. To do this, we'll need two parts, a random animal and a random number. For the animal, we'd just like to randomly select from a fixed list of animals. The sampled from strategy does exactly that, randomly return a value from a specified list. We can check what kind of values any strategy will generate by calling the example method. Now we can build a herd strategy by using our animals strategy and an integer strategy for the number of animals. To do this, we'll use a very handy higher order function that Hypothesis provides for constructing strategies that can build any object by passing in a function or callable. The first argument we pass to the build strategy is something to call to create the object we want. We're passing the herd class, which will be called to create instances of herd. The rest of the arguments are strategies that Hypothesis will use to get the arguments to pass to the herd class while constructing it. And now we can get random herds. Property-based testing is quite useful for parsing and serializing. The most common and general property is ensuring that data can make a complete round trip through serialization and parsing without changing. This is formulated as a property like this. Let's write a very simple serializer and parser for our herd object. The syntax will be the animal name and the number of animals separated by a comma. Now we can write our round trip test. Of course, we should go on to write more specific tests about the validity of the parsing and serializing, since the property can still pass with incorrect implementations, but it's still very good to have this case tested. Another great use of property-based testing is for fuzzing, which is a technique to check whether some system is resilient to invalid inputs. Not only is this useful for unit testing, it can be great for integration tests against network services. For example, say we have some server that exposes an API over HTTP. We can easily get Hypothesis to generate all sorts of inputs to our API server, such as URLs, HTTP request headers, and JSON request bodies. One very easy property to validate is that for any random input we send, the server should never send back an HTTP 500 code, which indicates an internal error. This is a great way to find areas in your web app where you haven't done enough input validation. Since I don't really have time to write a whole API service here, let's instead try fuzzing our herd parser and make sure we don't get back any strange errors. First, we'll update our parseHerd function to raise a syntax error in case it couldn't parse the input. Then we'll write a test for our parser that uses fuzzing. Here we should either expect a valid herd or a parse error. Well, it turns out we forgot a case. Hypothesis randomly generated a string containing a single comma, and the defensive programming we added to our parsing function wasn't good enough. Splitting the string containing only a comma produces a list of 2 empty strings, and calling int on an empty string raises a value error. So we'll have to protect that in the try block as well. And now our test passes. One last feature I'll touch on is the example decorator. This lets you manually specify some inputs to your functions that you want to make sure are handled. This is good if you know of some obvious edge cases ahead of time that may be difficult for Hypothesis to randomly generate. For example, if you have a silly function like this, then example will be very handy here. This way we can be sure we're covering the case where the user guessed correctly. One last point. Hypothesis integrates seamlessly with whatever test framework you use for running your tests. You can use the given decorator on any function or method, whether you're using py.test, nose tests, or the standard library's unit test module. This is because it simply wraps up your functions with some additional logic that's transparent to the test runner. Hypothesis is a very rich library with a ton of features, and I've only barely touched on them. The documentation at hypothesis.readthedocs.org is very thorough and easy to read, so I strongly recommend checking it out if you're interested in this type of testing. This lesson will introduce Effect, a system for isolating effects in your programs. Effect is a library that codifies a very rigorous approach to purely functional programming in Python. While we can get pretty far by just using pure data structures and objects and avoiding spurious mutation, Effect allows you to take functional purity about as far as you can go with Python by encoding your effects with pure functions. That's very abstract talk, so how does this work? Let's take a look at an example. This function has 2 side effects. The first is the call to raw input, which reads input from the terminal. This is a side effect because this function will do something different depending on what the user enters. The second is the call to print, which causes an observable effect on the world. We can't use equational reasoning with either of these. So how can we increase the purity of this function? Well, there are incremental measures we can take. We'll factor out some of the code into pure functions so that we can easily reuse it and test it. Here we've extracted a complement function. This way our little program has a functional core and an imperative shell. This is a very useful thing to do because pure code is much easier to reuse in other parts of your codebase and much easier to test. But can we go even further? Our main function still has those print and raw input side effecting functions. What we can do is instead of having the function immediately perform these actions, we can instead represent the actions as data and return them from our functions. One example could be that we want an HTTP client library that instead of having a method that performs the HTTP request, it could instead return an object representing the HTTP request to perform. Or in terms of our own example, we could have a function that returns an input request. Here we assume some input class exists, which represents a request to read some input from the user. We can code up this input class. All it needs to know is the prompt. I'm going to add an EQ method to this object since we'll need it later. With purely functional programming, it's very convenient if all of our objects support value-based equality. Now let's call main. As you can see, it's simply returning a pure object that describes the effects to take, and it always evaluates to the same thing. The next thing we do in our program is calculate a complementary message based on the name. But so far, we only have some effect object, which doesn't have the result. So how do we deal with that? Effects have an on method, which is a higher order function that accepts a function to call when the input request has been performed and the result is available. This way we can write code that makes requests and specifies what to do with their result all in one place, just as normal. The on method returns a new effect, which we can later perform. This interface is explicitly asynchronous, but it turns out there's a nice way we can write much more imperative looking code that's still completely pure, using Python's advanced generators. As you can see, this is very close to the original code. So what's the actual difference here? When we call this function, instead of immediately printing the prompt, requesting the name, and printing the complement, we instead get an effect object. So we know that we can use on to attach callbacks to process the result of an effect, but in this case we're done with all the result handling. It's time for us to actually perform the effect so that we actually interact with the real world. For that we use a perform function. In this case we'll use sync perform, which performs the effect and returns when all callbacks are complete. We're almost done. We need to define a dispatcher. This is the object which actually describes how objects like input and print are performed. Let's define print since we haven't done that yet, and then implement some functions to perform those objects. Now we have all the performer functions we need. We just need to create our dispatchers so that when we perform the effect, the library knows how to find the functions that perform those input and print objects. Now that we have our dispatcher, our program should work. I'll have to switch to the terminal to demonstrate the input and output. Okay, that sure was a lot of work just to get a simple 3-line program to run, so why bother? Well, all that indirection can be quite useful. The primary benefit is that our main function, which previously had side effects, is now completely pure and has all the attendant benefits of functional programming, like the ability to do equational reasoning. No matter how many times we call main, we'll always get the same result, and no unexpected side effects will leak out. The critical thing to understand is the difference between the performance of an effect and the representation of one. We can even use the effect we get back multiple times without calling main again. Here we've twice performed the effect that the main function created without having to call main twice. But that may not be very convincing. The two very practical areas that this kind of code improves are testing and modularity. Let's write a unit test for our main function. If we were writing this for our original imperative version, we'd have to do some nasty global patching of the raw input and print functions, or hack the sys.setIn and sys.setOut attributes. Since our function now returns an effect, we have some very nice tools for testing it. First, let's add an EQ method to our print object, since I seem to have forgotten it. Now we can use an object called a sequence dispatcher, which is a very useful utility for testing our effects. This is where we needed the value-based equality in our input and print objects. What sequence dispatcher does is ensure that the provided effects are run in the specific order they're listed, and allows specifying the results of each effect in turn. This way we don't need to mock or patch any objects in our unit tests, and we get a nice declarative way to describe the sequence of effects our functions are expected to have. The other main benefit of effect, which is modularity, is also what enables this great unit testing support. Imagine if the print and input objects were separated from the performer functions in different modules or even libraries. We could implement different performers for those same objects that do things other than just use raw input and print. For example, they could use a GUI library to prompt the user visually or a web server to render a web page. Another example would be an HTTP client library that supports either using Twisted for I/O or the popular requests library. By specifying our effects with the effect library, we get some pretty extreme separation of concerns. This separation of effects from performers is also how Sequence Dispatcher works. It provides alternative performers for your effects that don't actually have an effect on the world, so that they can be tested safely. That's all I'll cover about effect for now. Documentation is available at effect.readthedocs.org. It's fairly thorough and covers what I've talked about here in more depth. There's also integration with the Twisted framework available in the TX Effect project, which is available at txeffect.readthedocs.org. More examples are available in a separate repository on GitHub. To demonstrate the techniques and libraries we've learned about, I'm going to implement a simple game which we'll add on to throughout the course. I'm personally a big fan of interactive fiction, also known as text adventures, so I'm going to implement a really simple text adventure game. If you're not familiar with this kind of game, it's generally presented with a text-only interface where descriptions of environments and objects are displayed on the screen, and a command prompt is used by the player to control a character in the game world. Often these environments are laid out abstractly as a connected graph of rooms that the player can navigate by entering cardinal directions like north, east, south, and west. A classic example of this kind of game is Zork, which was initially released in the late 70s and commercialized in the 80s. Here's an example transcript of gameplay early on in the game. Here the player enters the look command to see a description of the current location and interacts with some of the objects in the world. Since we have limited time in the course, interactive fiction will fit well, since it's really easy to implement a simple version of a game like this. Of course, modern interactive fiction is often much more refined and intricate compared to what we'll be creating, but we'll write some code that approximates these types of games. The goal will be to have a simple world in which the player can control a character by moving around, reading the descriptions of rooms, and so on. We'll add a tiny amount of challenge to the game by adding some sort of trivial puzzle for the player to solve to achieve some goal, and I hope that after we work on it, you can play around with the code to extend it with whatever game features you want. The core logic will demonstrate some simple pure functional programming techniques, and show you how you can change the world per se, without actually mutating any objects in Python. We'll do this by representing the state of the game as inputs and outputs of pure functions. After that, we'll go on to extend our game with a user interface as well as some database persistence to demonstrate various ways in which we need to deal with real side effects in our purely functional programs. This lesson will cover the basics of implementing the core logic of a simple interactive fiction game. So let's think about what we want to do in our text adventure. We want the player to be able to view a description of the location that they're currently in. Each location should be connected to other locations, and the player should be able to move from location to location by selecting a direction to move in. This implies that we need to keep track of the current location of the character, and we need a way to move from a location to a connected location. So we'll need the following: a location class, which has a name and textual description, as well as the exits, which should be a mapping of direction names to locations. We'll need to collect these locations into something we'll call the world, and we'll need a GameState class, which has a reference to the world and the current location of the character. We'll also have a move function, which moves the character from a location to a connected location based on the direction. So let's get to coding. First, we'll create our room class. I'm going to be using the P-class feature of the Pyrsistent library. P-classes give us a number of benefits. We can easily declare fields without having to initialize them ourselves in an init method. We can get some simple type checking on the values of the fields. We can automatically get value equality on any instance of a P-class, as well as hashing. And we can modify instances in a purely functional way with the set method. So here's our location class. We can define a couple of locations for the player to move around in. Next, we'll define our GameState class, which only needs to hold a reference to the player's current location, and also a world, which is a mapping of location names to the location objects. You may be wondering why I decided to make the world a mapping of location names to location objects. Notice also that the exits field of location objects is a map of exit name to location name. It may make more intuitive sense to describe the exits as a map of directions to location objects directly, instead of just their names. The problem with this is when it comes to circular dependencies between locations. It'll be quite common to have some location which you'll be able to leave to get to another location, and then go back to the original location. If we modeled the exits as a map of exit name to location, the only way we'd be able to create these objects is by mutating them after we define them, like this. Not only does this mean our data structure won't be purely functional, it's also just a tedious and error-prone way to specify the exits. So instead, we use a mapping of direction name to location name, which allows us to effectively have forward references to locations that we haven't defined yet. We'll use the world mapping in our GameState object to resolve these references at runtime. As an aside, that's not to say that it's impossible to have a purely functional model of locations that form a cyclical graph. We could implement a pure function that returns such a graph, but in Python we'd have to implement it by using hidden mutation. In a language like Haskell, we'd be able to take advantage of non-strict evaluation to describe a graph like that purely. Regardless, we'll stick with the simple mapping of names to locations. So we have some rooms in our world class defined. Let's create an initial world object as an example. Since we're building up some pretty deeply nested data structures now, the default string representation is getting pretty unwieldy. It doesn't even fit on the screen. So I'll write up a little function to pretty print the game state, which we can eventually use to display the game to players. We want to display the name of the room, the description, and any exits in the room, all formatted nicely. I'll use a generator comprehension to go over the exits in the room and save those in a new line delimited string called exits. Then I interpolate all the rest of the data from the state into a template string to create the final rendered result. Alright, this is really coming together now. The only thing left is to add a way for our character to move between locations in the world. How will we do this without mutating the world? We can just create a new one. Our move function will take a game state and a direction and return a new game state with the location set to the new location that the player has moved to. We deal with invalid directions by returning none from the function. We could just return the same game state, but by returning none, we signal that the player couldn't be moved, so a user interface could display some useful error message. If there were multiple things that could go wrong with this function, we could use exceptions, but I think just returning none should be good for now. Let's test our move function. Okay, so since we moved east from the initial state, which had us in the house, we end up in the street. And if we move to a bad location, we just get none. Alright, that's the core of our game. We can walk around rooms in the world, and we've shown how we can manipulate the world in a purely functional way. I recommend trying to play around with this code to add more features. Just remember to think in functional terms. If you need to effect change on the world, write functions that process game objects by taking them as arguments and returning the modified version as a result. You can find this file as core.py in your working files directory. In this lesson, we're going to extend the simple text adventure we developed with some more features. We'll get more practice with the concepts of FP and go a little deeper into design of functional data structures, while learning some useful tricks with the Pyrsistent and Toolz libraries. You can find the code we'll start with in the core.py file in your working files folder. By the end of this lesson, we'll produce all the code that you can find in core2.py. We're going to add a couple of features to the game's codebase. I want to introduce more dynamic features to the data model of our objects, since that's usually the point of contention when it comes to functional programming. How do we change things when we can't mutate state? First, we're going to implement the idea of props that exist in locations in our game world. Then we'll implement an inventory for the player so we can pick up those objects. And finally, we'll implement a simple lock and key puzzle that requires the player to find a key before they can go through an exit. First, let's work on our game's data model. We'll need a new thing class, which we'll just give a name field for now. Our location object will have a new items field, so we can say what items can be found in a location. This field is a mapping of thing names to thing objects to make it easy to look them up by name. Let's update the render function so it can show the items in a room. This code is already pretty gnarly, so let's refactor it a bit. I'll create a template for the room description as a top-level constant, and then I'll update the render function to use it, while also adding the location's items. Now we can put a thing in one of our locations. Let's create a rusty key and put it in the street. This will be the key for our lock and key puzzle. Now let's see if we can see it in the street. We'll need to move east from the starting location and then render the game state. Great, we can see the rusty key in the street. So now we want to be able to pick this key up. We'll need a couple things for that. First, we'll add a field to the game state to keep track of the character's inventory of items. This will be a field containing a p-vector of the player's items, and so we'll need the p-vector field function from Pyrsistent. There's a bit of code in the move function that we need to update since we added this field. Instead of creating a new game state object, we should have been calling the set method with only the attributes that have changed. This way, if there's some data in the inventory, it will be maintained in the new game state when we move. It really should have been done this way from the beginning. To allow the player to see what's in their inventory, we'll add a line to the rendered output that shows it. Let's make sure that we can at least see the empty inventory when we render the room. Okay, so now we finally get to the important part, implementing the function for actually picking things up. This function will take the state and the item name and return a new state. First we'll look up the item if we can find it and return none if we can't. Now we need to do two things. First remove the item from the location and then add it to the player's inventory. In order to remove it from the location, not only do we have to remove it from the items map, but we need to update the location to point at the new items map we get back. Now we'll add the item to the player's inventory. Finally, we modify the state to have all the new data and return the new state. This isn't the prettiest function, and we can improve on it, but let's just make sure it works for now. First we'll create a game state representing the player having moved to the east, then another state after we pick up the rusty key. Let's see if our take and render functions work correctly. Before we pick up the key, we can see it in the street, and after we can see it in our inventory and no longer listed in the location. Great. But there's a bug in our implementation, and you may have noticed it. I'll demonstrate. After taking the key and then moving around, it's still in the street and simultaneously in our inventory. We've got an item duplication bug. The problem here is that we actually have two copies of the street location in our game state. One in the location field, which represents the player's current location, and another in the world map. So to work with this model, our take function will have to update the world as well. Let's see if that fixes our bug. Alright, so that's fixed it. But this take function is quite a beast. It's not that long, but dealing with replacing all of the outer objects after we update inner objects is pretty tedious. Fortunately, Pyrsistent provides us with a nice way to update deeply nested structures through a method called transform. This method takes a path to a particular piece of data in a nested structure and a function to call on that value to produce a new value. We can use it to easily change the items map inside the current location, which is inside the game state. The transform method is available on P classes, P maps, and P vectors, and it can traverse through all of those types. We can also pass additional alternating paths and functions to update more data, like the player's inventory. But when we try to deal with the world mapping, we run into a problem. We don't have the new value of the location that transform has calculated for us in the first manipulation that we requested. We could recalculate the location with updated items, but this means we're duplicating work by removing the item from the items map twice. For now, we can just update it in another step, using the newly updated location in the world. Let's make sure this works with our little test case below. Great, it still works, and the code is a lot shorter. But this multiple update problem has really been hounding us in the implementation of Take. Really, our problem is a poorly designed data model. It might be okay in a typical imperative object-oriented design, but it's not working out so well with functional programming. The benefit we get in not needing to worry about values changing out from under us also means that when we do want them to change, we need to be more thorough. But we can simplify this design a lot by just not duplicating that location object in multiple places in GameState. There's a really simple solution to this problem, and it's the same one we used when designing our location's exits field, which is a map of exits to location names instead of location objects. We just need to update GameState to hold the current location as a name instead of a location object. Now we can define a function to look up the location object based on the game state. We'll use a little object-oriented idiom here and create a location property on our game state class so most of our other code doesn't need to be updated. We still need to update a couple of things though. First, the move function, since it was updating the current location, and then the take function, since it no longer needs to update the current location. Let's make sure everything's still working. We'll update our game state creation to use a name, and then rerun our test. Finally, our code has gotten significantly simpler with this new model. So far, we've implemented items in the world that we can pick up, and we've fixed our game's data model to be much easier to modify. We also learned about the transform method in the Pyrsistent library. That's a good amount of ground to cover for now, so we'll stop here. In this video, we'll implement locked exits that require keys to traverse, and we'll learn some ways to improve the expression of actions in our game. At the end, I'll describe some exercises for further improvements to the game that you can make on your own. So we're getting close to having an actual challenge in our game. We have keys but no locks to open. We'll need to specify that some exits require a key to get through. I'll keep this simple so we don't need a command like unlock. Instead, we'll just check that the character has the key when they try to go through the exit. We can implement this pretty easily by augmenting our exits data with required keys. We'll do this by changing the value of our exits field to be a tuple containing the item required to pass through the exit in addition to the destination location's name. We'll just use none when no key is required to pass. We'll need to update all the code that uses the exits. That's just the move and render functions, as well as the locations we created for our game. While we're updating render, let's make the format a bit more descriptive. We'll create a little nested function to handle rendering a single exit and include the destination as well as whether it's locked. Then we'll use a list comprehension to map our render exit function over the exits. Now we'll finish implementing this feature with a change to the move function to honor the locked exits by checking if the character is carrying the required item when moving through an exit. For simplicity, I'm just returning none when the player doesn't have the required key, but this should probably raise a specific exception. Before we can test this, we'll need to update our location objects with the new format for exits. We'll create a basement under our house in the game world, which requires the rusty key to enter. And finally, we'll add the exit to the basement, which requires the key. Let's try a few different test cases. Moving down from the initial state should return none since we don't yet have the key. Going to pick up the item and then going back to the basement should work. Alright, we've actually got a puzzle in our game, though it's a trivia one. That last expression was quite a beast. While it's nice that we can express these chains of commands with a single functional expression, it's becoming tedious to write out these long lines. One pattern that we can improve upon is moving multiple times. Instead of writing this, it'd be nice to have something like this. This makes it much more clear what's happening than the deeply nested expressions. How can we do that? It turns out that this is trivial to implement with Python's reduce function. The move function we wrote is already perfect for passing to reduce. This folds the move function over the given directions, with state as the initial accumulator value. Reduce will call the move function with the state and a direction from the move list, and then take the result of that and pass it to move again with the next direction, and so on. Let's rewrite our full game solution with this function now. It's a little bit nicer, but because we have to put the take command in the middle, it's still pretty difficult to follow. It'd be really nice if we could lay out these functions in order so that the later commands go after the earlier commands, instead of nesting the earlier commands inside the later commands. It turns out there's an extremely useful higher order function in the Toolz library that does exactly this. The general idea is called threading, not to be mistaken with the idea of concurrent programming. Rather, it's about threading a value through a series of functions. In Toolz, this function is called thread first. It's named that way because the given value will be passed as the first argument to each function in turn. You can use it like this. This function passes the initial value you give it to the first function in the list. Then it takes the result of that first call and passes it as the first argument to the next function, and so on. So the number 1 is first incremented to become 2, and then 2 is passed to double to become 4. It also provides a handy syntax for passing additional arguments to each function, by replacing the functions being passed with tuples of a function and remaining arguments. For example, if we're using functions that take additional arguments like add and mul, then we can thread our value through those functions like this. Here the number 1 is being passed to add along with the number 5 to get 6. Then that's passed to mul along with 3 to get 18. So let's try applying this to the problem we're having with commands in our game. I was actually surprised to see how nicely this turned out. We can express our commands in an easy to understand imperative style, but this whole expression is purely functional, just a pipeline of state manipulations. That's all for the code changes in this lesson. Now I want to give you some ideas for how you can extend this game with new features. Imagine having a new type of exit that takes you to a different location every time you go through it, as part of an enchanted maze. Consider how these exits should be specified in our game model. Perhaps the tuple that we currently use to hold the key and the destination could be replaced with a more rich object. Also consider how that object will need to change over time as we go through the door. Another idea would be to implement a non-player character that you have to talk to or otherwise interact with. Also, our data declarations are getting kind of verbose. You could implement a simple function that gives it a nicer syntax. For example, maybe we could elide the none that we pass for unlocked exits. It'd also be nice to have a little function to create a world and game state from a simple list of locations. Lastly, try to make this game multiplayer, but don't worry about things like networking. By focusing on keeping the code purely functional, it should actually be easier to keep the concerns of networking separated from the core game logic. The important question is, how will the code need to be refactored to support multiple players? We learned about a few things in this lesson. There was a very useful transform method in Pyrsistent for doing deep data manipulations on nested data structures. We also talked about representing complex interconnected graphs of objects in a purely functional way by denormalizing any data that needs to be changed over time. And finally, we simplified deeply nested computations with the thread first function in Toolz. You can find this code in the working files for this chapter as core2.py. This lesson will cover unit testing of functional code using the text adventure we developed in previous lessons as an example. If you haven't watched those lessons, you can find the code that we produced in the core2.py file in the working files folder. So far, I've been developing the text adventure game interactively, which functional programming lends itself very well to, since as we make changes, we don't need to worry about mutable state that we need to constantly clean up or reinitialize. But we should really record all of our experiments properly as unit tests so it's easy to run them later. We'll create a small test suite in this lesson to do that. I'll be writing the unit tests in this lesson as simple top-level functions, which happens to make them compatible with both the nose and py.test commands. However, everything in this lesson should be easily portable to other testing environments, such as the standard library unit test module or Twisted's trial. We have a few functions we want to test, and each function may have multiple cases, but not that many. First, let's look at the take function, since it's relatively simple. It has two interesting cases. One where the given item name is successfully found in the current location, and another where it's not found. Let's write up a quick little test for that negative case first. Okay, that was simple enough. Now let's test the case where we actually pick something up. We have a lot of duplication between these tests, so let's factor them out to keep them nice and concise. I'll just copy the game data we have from core2.py into our tests to expedite this part. Notice that I just extracted the code that creates the thing, location, and game state to top-level definitions. Most of the time we want to avoid that in unit tests since we want to make sure all of our tests are isolated. But since we know that we don't perform any mutating operations on these objects, it's totally fine to make them global variables. The mantra that global variables are evil is mostly just about global mutable variables. This is yet another simplicity we gain by using functional programming. Alright, let's move on to the move function. This has 4 interesting cases. I'll start with the negative cases since they're the simplest. First, we have the case in which the direction given is completely invalid. Then we have the case of attempting to go through a locked exit when we don't have the required item. Then we move on to the success case, where we successfully move through an unlocked exit. And finally, we should be able to move through a locked exit when we have the key. Testing the invalid move is simple enough. We get back none when we can't move in a direction. The case of testing a locked door is just as simple. Now the success cases, when we move the location name attribute of our game state changes. This test shares a game state with the previous one, so we can refactor the expected state into a top-level global named inStreet. Finally, we can test moving through a locked door with a key. We'll need the key for this test, and we created a state for that in our take tests above as well. We can also reuse that one. Alright, I believe we've covered all the interesting cases of our functions. If you're interested in testing the render function, I'll leave that as an exercise. Consider how simple all of our tests turned out to be. Each of them is a single expression compared to a single expected result. It's true that our game logic is primitive, and that's certainly a big contributor to the simplicity of our tests. But the fact that our game is made up of pure functions and values that support value equality is what lets us keep the tests simple. If this were a typical imperative object-oriented design, even with a similarly primitive game, we'd have to be more careful about our shared data. Each test would have to run some command, and then check how those commands mutated some state somewhere, instead of having everything nicely encoded in return values. As the application under test grows more complex, the benefit we get from keeping it purely functional will increase. If you're interested in experimenting with these tests, you can find them in the testgame.py file in your working files folder. In this lesson, I'll introduce the Hypothesis Stateful Testing API in preparation for using it to test our game's simulation code. The Hypothesis library provides a system for generative testing, also called property-based testing. Usually, generative testing is about generating random data which you can use to test your functions. This grants us the benefit of not being restricted to our human conception of useful test data. Quite often, the Hypothesis library can generate much more devious inputs than we can come up with when writing tests. In addition to just being able to generate data, though, Hypothesis has a really useful feature in the hypothesis.stateful module. This module gives us a way to generate sequences of operations on data. This is really useful when we have multiple functions that act on the same state. I'll jump in with an example and then explain. To use the stateful testing system, we create a subclass of rule-based state machine, and then add some methods decorated with the rule decorator. When we run this test, Hypothesis will instantiate the class and generate many different programs or sequences of rules and run them. We can see the programs that Hypothesis generates if we enable debugging when we run the tests, which I've done. I've also limited the number of steps per program to 10, when the default is usually 50, just so the output is more readable. Hypothesis has generated 200 different programs of 10 steps each using our inc and dec methods. As we can see, not only does it try some programs that switch between different calls, it also tries cases like sequences made up of 10 calls to the same function. This usually doesn't matter, but sometimes it can find some pretty subtle bugs. Okay, let's extend this example a bit. Let's say we want to add a rule that divides some number by whatever the current number is. Let's run that and see what happens. Hypothesis has pretty quickly found out that div won't work when the current number is 0. The best way to solve this problem is by using a precondition. The precondition decorator takes another function that must return true or false, and uses it to determine whether a given rule is currently eligible for use in the program. Note that this is much better than using the Hypothesis assume function, since it makes it much more likely that a useful program will be generated. And now our tests pass again. We can see that it generated some programs that use div correctly. There's one more change that I'd like to make to this code. Currently, it's very imperative feeling. Each method does some operation in terms of the state attribute, and then mutates the state attribute on self. I'd like to abstract away this mutation. One reason to do this is that if we forget to assign it in one of our rules, we may end up with tests that pass when they otherwise wouldn't. We can abstract this away by writing another decorator to do the work for us. I'll change the rules first to show you what using it will look like. We've changed the rules so that they accept the old value and return the new value instead of having them use and mutate self.state. Now let's define the stateful decorator. And let's run it and make sure it works. Great. So that's pretty simple. Note that I used the wraps decorator from the functools built-in module. This is useful for defining decorators since it ensures the name of the decorated function is the same as the original function, which is useful if you have code that prints out names of functions, as Hypothesis does when it has debugging enabled. Anyway, now if we look at our div implementation, it's a bit ridiculous that we have more decorators than lines of implementation. Let's make this a bit simpler by defining a single decorator that composes stateful, rule, and precondition. I've called it sRuleP for stateful rule with precondition. This is literally just the composition of those three decorators, so the implementation is nice and terse since I used the compose function. Now our code can be cleaned up. Now our test case is nice and terse again. Finally, I'll explain how these test cases should be run with test runner tools like py.test or trial. Most of these runners support standard Python unit test cases, so the easiest way to do this is to expose the test case attribute of our rule-based state machine at the module level. If your test runner doesn't support test cases, then you can just define a test case in whatever way you need to and call the runTest method of this test case instance, as I've been doing to run these tests manually. Alright, that's it for this lesson. We've learned how to generate programs that act on some state with Hypothesis, how to use preconditions to ensure our rules are only run when they can be, and we've done some abstraction to keep our tests nice and clean. In this lesson, we'll be writing tests for our game's simulation code by using the Stateful testing API in Hypothesis. We'll be testing the code in core2.py, which you can find in the Working Files folder. I'll briefly recap the game's code before we get to the testing. In the simulation code in core2.py, we represent the state of our game with the GameState class. To perform actions in the game world, we have functions which take a GameState object and return a new modified version. This is exactly the kind of situation where the stateful testing feature in Hypothesis can shine. It can help us create random sequences of calls to these functions to test all sorts of edge cases. In addition, we can add assertions to run after each of these functions are called to make sure that they always do the expected thing. So let's get right into the code. I'm going to be using some functions that I defined earlier as part of the lesson on stateful testing with Hypothesis. Stateful is a decorator that gives us a way to define purely functional rules that accept some state as a parameter and are able to return that state as a result. sRuleP is a convenience function that composes the rule, precondition, and stateful decorators into one decorator. So that's the boilerplate. Let's define our state machine. We're declaring a rule-based state machine subclass that has the initial state of the game assigned as the state attribute. The stateful decorator will make all of our rules work in terms of that state by passing it to the functions and assigning the results to the attribute. So let's write our first rule. We'll do one for moving around the game world. We need to write some code that will work no matter what the game state is. We can't assume that we'll be in any particular location. All of the locations in our game have exits we should be able to go through, but we don't want to just hardcode them. The best way to deal with this is to pick a random exit from the current location as specified by the game state. In Python, we usually use the random.choice function to pick things randomly. But in Hypothesis, having randomness in our tests can cause problems, especially when there's an error and it tries to simplify the examples that cause the crash. So Hypothesis provides a special API for making random choices. By using the choices strategy, Hypothesis will pass a function to our rule that we can use to randomly pick an item out of a list. We'll use it to choose one of the current location's exits. Here we're getting a direction to go in, that is, the name of an exit. And then we call move with the state and that direction. We want to have a meaningful test, so we'll check if the new state has us in the destination. This looks like a reasonably complete test. Let's see what happens when we run it. I'll just put a call to the runTest method at the bottom of our module so we can run it as a script. Normally you'd just expose the test case attribute so your test runner can pick it up. An error. Okay, so let's take a look at what happened. We have an exception that indicates that our move function returned none, which we know it does in the case of various problems. Sadly, we never implemented custom exceptions that tell us exactly what went wrong, but fortunately, Hypothesis provides us enough information. If you look at the first line, you can see the program that Hypothesis generated that caused the error. It was able to simplify the buggy program to a single step, a call to the move function. The second line, where it says choice number 1, is the result of our call to choice. It's really nice that Hypothesis automatically shows us all the results of calls to choice in our program. This gives us enough information to know exactly what went wrong. In our game, the first location has a locked exit, one that requires a special item before we can go through it. Our test tries to go through any exit, not just unlocked ones, so our rule fails because we can't move down. So how do we solve this? Well, we just need to make sure we choose an unlocked exit in our rule. This unlocked exits list comprehension filters out any exit that has a required key. Now let's run our test and make sure it works. Great, no error. Our move rule is now done. So what else can we put into our tests? Well, let's say we want to explore the entire map. To get through the locked door to the basement in our game, we need to be able to pick up the rusty key. So let's add a rule for picking up items we find in the game world. This rule is very similar to the one for move. We use the choice strategy to choose a random item in the location, take it, and then run some assertions to make sure that it's now in our inventory and no longer in the location. Let's try running this and see what we get. Well, there's another error. Again, Hypothesis was able to trigger the error with only a single step. It's very good at finding simple reproducers. All it had to do was run take on the initial state. The exception is telling us that we couldn't choose from an empty sequence, which makes sense since the starting location in our game doesn't have any items on the ground. To solve this problem, we need to use preconditions. We want to make sure that the take rule is only ever considered when there is at least one item in the current location. Our sRuleP decorator allows passing a precond argument to specify the precondition. This lambda function returns true only when there is at least one item in the current location, and that should be enough to make our test pass. Alright, so we're able to move around the world and we can pick up items. The only thing left is to try to make our way to the basement, since we can theoretically pick up the key necessary to go through it. This one will be a little bit more tricky. I'll start off with the main body of the rule. Here I'll assume we have a function called eligible locked exits. We want this function to return all the locked exits for which we already have the key. And the rest of the rule is identical to the move rule. Call move and make sure we ended up in the right place. So there's the implementation of the rule. We also need a precondition to ensure we only try to run this rule when it's appropriate, but first I'm going to implement that eligible locked exits function. Here we go through all the exits in the current location and filter by those that require a key that we already have in our inventory. Now we have one more thing to do. Add the precondition to the new rule. We only want to run this rule when there are actually some locked exits for which we have the key. So our precondition can just check if eligible locked exits returns at least one item. Let's make sure this works. Okay, it didn't raise an error, but I'm not completely sure that all of our rules are being run. We might have made an error in one of our preconditions, which would prevent the rules from running. To satisfy ourselves, we can run the test with debugging enabled and check if move through locked door ever gets run. We can do this by specifying the hypothesis verbosity level environment variable when we run the tests. If you set it to debug, then hypothesis will print out every single step taken in every randomly generated program. We can search this output to see if move through locked door gets called. So here we see all of our programs. Hypothesis will generate 200 of them by default. I'll search this output for our rule. Great, there are actually lots of calls to it. Looks like we're just fine. Okay, we now have 100% coverage of all of our simulation actions in our game code, and we did it in a way that's flexible enough to work with any map we create. So that wraps up all the code in this lesson. I'd like to point something out in conclusion. If you look at any of our rules, they look very similar to test cases we might write normally. Call some function and then make sure that the result is as we expect. They're only marginally complicated by the use of hypothesis for generative testing, and by going to this extra effort, we aren't limited to the test inputs that we can think of ourselves. Hypothesis will find most of the edge cases that we'd be able to come up with, and it exercises our actions quite a lot more than we normally would in manually written tests. When I'm writing test cases for my own code, I usually find that it's quite easy to convert them to use hypothesis, just by getting rid of all the hard-coded data by using strategies to generate data for me. Even if you don't do much more than that with hypothesis, you can still get a lot of benefit. In this lesson, we'll implement a trivial user interface for our text adventure. The interface will be a simple command prompt into which the player can type commands. You can find the code for the game in the core2.py file in the working files folder. If we look at the code in core2.py, we'll see that our game currently has two commands that we want to expose to the player, take and move. Take gives us the ability to pick up objects in the game world, and move allows us to move through exits to other locations. We'd like to expose those commands with a simple parser that allows the user to type things like take apple and move east. Let's consider the structure of the interactions. First, we want to render the current location and print that description to the screen. Then we want to prompt the user for input, act on that input, and start all over again. The typical way to do this is with an infinite while loop. Let's write a main function that represents just that loop and delegates the processing to another function. Starting with some initial state, we'll call a step function with that state to handle rendering, input, and processing of commands. We'll have step return the new state of the game, and we'll continuously replace it and call step again. Now let's implement that step function. First we want to render game state. Then we'll parse the command and print a message about whether it was successful. We use raw input to get input from the user, or if you're on Python 3, just use the input function. Then we'll do some really primitive parsing on that input by splitting it on the first space. We only support take and move, and each one has a mandatory argument, so let's print an error if the input doesn't meet those constraints. And we'll return the state unmodified since we didn't do anything. Then we'll dispatch our input to the appropriate function. Our functions return none when there's an error, so let's handle that by printing an error message and returning the same state unmodified. Finally, we'll make sure to call the main loop function when this file is executed. Okay, I think that should be enough to try it out. I'll fire up my terminal and run the program. Okay, so at least it's rendering our first location. We should be able to move around, and we can pick up items in the world. It's really satisfying to see our game actually playable. Let's make sure we correctly handled the various kinds of bad input. Alright, so we get error messages and the state is unmodified. Let's make sure we get into the basement with our rusty key. Alright, we've made it. So if you want to play around with this code, then here are some ideas for things you can do. You could implement a quit command that exits the game, or you could implement a win condition, which automatically ends the game when you meet it, such as entering a specific location. For now, we just exit the game by hitting Control-C. Alright, so let's take a look at our code again. If you've been following along with my other lessons, you can probably tell that this is far from functional code. It's got while loops that change variables, it has side effects for dealing with input and output, and so on. But that's not bad. The core logic of our game is still purely functional and easy to test. Our game loop is just an imperative bit of code wrapped around it. This is really a powerful idea, and I like the way that Gary Bernhardt describes it as functional core imperative shell in his talk called Boundaries. By doing things this way, we only have to worry about the side effects in a very small part of our code, that is, the code that directly deals with those side effects. Our functional core is still easy to test and won't be easily broken by the spooky action at a distance which is endemic to imperative programs. But if we look closely at our step function, there's a lot more we can factor out into pure functions. So let's see. First off, we should be able to extract out the part that parses the command. So instead of just printing the error message in this code, I raise an exception. Exceptions are pretty iffy when it comes to functional code. In some sense, they go against the grain of functional programming since they're essentially a result that is not represented by a function's return value. On the other hand, with some wishful thinking, we can kind of pretend that an exception is just a special case of a return value which is automatically checked and propagated by callers. Another way to encode errors in a more purely functional way is with something called sumtypes or tagged unions, but I'm not going to get into that in this lesson. For now, we'll just use exceptions. Now our step function can be a little bit smaller. We can also factor out the part that dispatches the command to a handler. Now we can refactor our step function to unify all that error handling. So look at that, our imperative shell has become really small, and notably it only has a single conditional, the case of handling exceptions versus a successful response. Reducing the number of conditions in our imperative shell is important. The fewer conditions we have in a function, the fewer tests we need to write for it. And writing tests for the imperative shell is a lot more difficult than writing them for pure functions, since they often involve globally patching the I/O functions we make use of. And it's not just about testability. These functions that we've extracted are now usable in other contexts, meaning the code has become more modular. We may be able to use these exact functions if we write a different user interface, like a web app or a native graphical application. This is an important part I want to drive home. It's good to factor your program into a functional core and imperative shell, and when you do, make sure to analyze your shell for any possible bits of functional code you can isolate from the actual side effects. It's not always this easy, but it's worth it for the gain in modularity and testability. In this lesson, we'll discuss writing unit tests for imperative effectful code. We'll be testing the console-based user interface for our text adventure game. You can find the UI code in textui.py and the core game code in core2.py in your working files folder. There are a few functions in textui.py. The easiest ones to test will be the pure ones, parse and dispatch. Let's write some tests for those functions first. To test the parse function, we just need to pass in a string and assert that the resulting lists look right. Checking the error behavior of parse is a little bit more involved, since it raises exceptions. I'll make use of a PyTest feature for catching the exception in a nice way. Most test frameworks have some nice API for asserting that specific exceptions happen. We just want to make sure that the exception has the right message. Dispatch is also pretty easy to test. Again, just calling it and checking its return value. When we move east from the initial location, we should end up in the street. And when we take the rusty key, it should appear in our inventory. We'll also need to test the error case of dispatch. When we call dispatch with bad input, we expect an exception to be raised. Okay, so our pure UI functions were pretty easy to test. Now for the tricky stuff. We need a unit test for the step function. Since we want to test this code without actually printing anything or prompting the user for input, we need to do something about the use of the print and raw input functions in this code. The most common way to deal with this is by using the mock module, which is available in Python 2 by installing the mock package. In Python 3, it's built in as the unittest.mock module. We use the patch decorator to specify that we want the given name to be globally replaced with a mock object. We use a common trick here to override the print function as it's used within the TextUI module, by taking advantage of the fact that we can patch textui.print, and any functions within TextUI that refer to print will find the value we patched. We'll mock out both the print and raw input functions. The decorator then causes the mock objects to be passed as parameters to our test function. First, we specify that the raw input function should return a hard-coded value, move east. Then we'll call step with our initial state. Step will call the print and raw input functions and handle the move east command. We'll make sure the command was evaluated properly such that we end up in the street. Okay, so now we know that the move command actually took effect, but we need to make sure that the right info was printed out to the screen. First, we want to make sure that the initial state was rendered and printed. We do that by calling assert any call on the print mock object. Then we want to make sure that the user was prompted for input, so we assert that the input mock was called with the right prompt. Finally, we check that the OK text was printed. This is a relatively straightforward test when it comes to mocking, but as the code gets more complex, this mocking style becomes more difficult to maintain. But this is certainly better than the alternative of not even having a test for our step function. This is one reason why we want to keep our imperative shell code so small. I'll describe some details about the use of mock for testing side-effecting code. First, we have to patch globals in the TextUI module. This is pretty fragile, especially in cases where the patched names are imported. If the style of import changes, a test like this can break. For example, if we're testing some function in module A that uses a function in module B, our test will rely on the way in which A imports the function from B. If it does from B import F, we have to patch A.F. If it does import B and then uses the function as B.F, then we have to patch B.F. In that case, any other users of B.F will also get our patched version if they're accessing it through the module instead of importing it directly. This leads to really confusing test bugs that are very hard to track down. We could avoid the patching by explicitly parameterizing the print and raw input functions so our test can pass in stubbed out versions. This can sometimes be useful, but it's tedious and it requires us to clutter our functions with testing-only parameters. As for specifying the behavior of mocks, it's not always straightforward. We can assign to the return value attribute of the mocked function in simple cases, but if we need to return different values based on the inputs, we have to assign a function to a special side effect attribute and explicitly check the arguments. Lastly, it's not very easy to ensure the order of calls to our mocked functions. This is often very important in side-effecting code. For example, we really want to make sure that we print the room description, then prompt for input, then print the OK message. Any other order would be a bug in our application. Our current test doesn't verify that the functions are called in the right order. The way to do this with the mock package is to create a side effect function that appends its input to a list. At the end of the test, you then need to check that the list has the expected order of calls. Here's an example. As an exercise, you can try changing our tests for the step function to use this technique to ensure that the print and raw input functions are called in the right order. Now, some of these problems aren't universally true for all forms of mocking. The less popular mocker module actually has an easy way to define return values based on arguments and a way to ensure that functions are called in an expected order. But at this point, the mock library is by far the most popular tool, especially given that it's been moved to the standard library in Python 3. The one problem that mocking libraries can't solve is the difficulty of dealing with globally patched functions. It's always a risky scenario. Parameterizing dependencies, while it ends up being more work, is one way to avoid that problem, but it also becomes tedious with more complex code. So that's all I wanted to cover in this lesson: how to test our imperative shells using the mock library, and a warning about some of the limitations of doing it this way. I think that even given these limitations, using the functional core imperative shell model of application design limits the difficulty we have to put up with when dealing with side effects. So this is a great way to design our apps. However, I think there's a brighter future in functional programming where we can avoid these problems even more, but that'll be covered in other lessons. In this lesson, we'll learn about the SQLite library. I want to cover this as an example of using third-party imperative libraries in a mostly functional application. SQLite support is built into Python and is already available as the SQLite 3 module, whether you're using Python 2 or Python 3. SQLite is a simple and fast embedded relational database that uses standard SQL syntax. It can store data either in files on disk or in memory. It's great for most scenarios in which you don't need multiple machines to have access to the same database. I'm going to assume very basic knowledge of SQL in this lesson. If you don't know SQL, you'll still probably be able to follow along, since I'll only use really basic features. But there are a lot of great references online if you'd like to learn more. I'm just going to cover the basics of using the SQLite 3 Python library as is. The API is imperative and implicitly effectful, as a matter of course for Python libraries. Afterwards, we'll see how this interacts with our own purely functional code. I'm going to be using our text adventure as the running example here. You can find the code in core2.py. I'll also make use of a couple of definitions in testgame.py. These files can be found in your working files folder. So what are we going to do with SQLite? We're going to implement a storage layer so our game state can be saved and loaded. Here are the effectful actions we'll need to perform as part of this layer. We'll need to create tables to store our data, and to save the data, we'll go through all of the locations and game state and insert rows into those tables. To load the data, we'll query those tables and create location and game state objects. I'll give a caveat up front. If you're familiar with relational database design, I'm not necessarily going to use the best practices in this lesson, because I'd like to keep things simple. However, the code we write will definitely be suitable for a small game like ours. Let's just dive into some code, and I'll explain as we go along. First, we'll need to create our database tables. I'll just write out the SQL statements we need as top-level constants, so the functions we write are nice and short. The location table will be the most complex, since locations have a lot of associated data. We need fields for the name, the description, the exits, and the items. We're using the name of the location as the primary key, which will be important later. I'm going to punt on coming up with a deeper representation of exits and items for this example, and instead just store them as blobs containing JSON data. It may be better to represent individual exits and items as separate rows in other tables, but I think this is fine for our little game. The state table is a bit simpler. We need the location name field to keep the current location of the player, and the inventory field will be a JSON blob of the inventory. If you look at the source code for Core 2, you'll see that these tables are pretty direct mappings of location and game state classes. Now I'll write the function that actually uses these statements. This function accepts a cursor object, which is basically a handle that allows us to execute SQL statements. Note that our setup function doesn't have a meaningful return value. We're really going all out with imperative programming here. Don't panic, we'll address that later. Executing a SQL statement with SQLite is pretty simple. Just call the execute method on a cursor with the statement you'd like to run. I'll show you how to get a cursor in a second. To open a file as our database, we just call the connect function from the SQLite 3 module with a file name. This returns a connection object. Then, to get a cursor with which we can execute statements, we need to call the cursor method on that connection object. Now we can set up our database. We should be able to query those tables and get back an empty result now. Okay, we've modeled our location and game state classes in a relational database. We'll take a break here. In the next video, we'll actually store some data in those tables. In the last video, we created a schema for our location and game state objects and wrote a function for setting up the database. We've seen that queries against those tables return no results, and that's not very exciting, so let's figure out how to save some data. We'll need some insert statements. For simplicity, I'm using an insert or replace statement here so that we automatically overwrite locations of the same name if they already exist in the database. This is why we made the name of the location the primary key earlier, and it relies on the names of our locations being stable. To denote values that need to be passed in when we execute the query, we use these question marks. We'll see how to provide those parameters when we write the function for saving state. Inserting into the state table is simpler. We just need the current location name and inventory. We'll need a delete statement to clean up the state table, since we're only going to keep one in the database at a time, and also queries for fetching data, which are quite simple since we're just loading it all at once. Now let's get down to business. We'll write a save state function that saves the game state object and all the locations in the world. We're only going to keep one row in the state table at a time, so first we'll execute that delete statement, and then we'll insert the new row, which needs two values, the current location and the player's inventory. I'm just storing the inventory as a simple JSON array of item names. Now we'll go through all the locations in the world and insert them into the database. Remember that we specified the items and exits columns as blobs which we'll store JSON in. Like the inventory, the location's items will just be a simple array of names. We have to use the persistent thaw function here, since keys will return a persistent p-vector, which the JSON module doesn't know how to serialize. Thawing converts it to a plain list. The exits are kind of complex, so I'll factor that serialization out to another function. Now that we have the serialized data, we can execute the insert statement. Okay, that's the whole save state function. Now for the exit serialization code. The format we'll use for saving the exits as JSON will be an array of arrays of 3 elements. The direction, the name of the required thing, or null if there is no required thing, and the destination. Here's a quick list comprehension to do that. I use a conditional expression for the required thing to return none if nothing is required to pass through an exit. Okay, so we finally have some code that we can try running to see if it works. Let's see if we have data in our database now. Great, we can see the data from our sample game made it into the database. Now we need to write the functions to load that data into instances of location and game state. I'll create a load state function that takes a cursor and returns a fully populated game state object. First, we execute the location query to get all the locations in the world. Then we build a world map based on those results. I'm delegating the parsing of the individual rows to another function to keep this one simple. Next, we'll load the state object. This one's simpler once we have the locations. I'm using the next function since we know there's only one row in that state table. The next function just grabs the first result from the iterator that execute returns. With the data from that query plus the world map we already created, we can create the GameState object. The first column is the location name, and the second is the inventory stored as a JSON array. Okay, so that's our load state function. Now we need a load location function, which will return a location instance based on the data in a given row. The exits are the most complex part, so I'll do that first. They're stored as a JSON blob in the third column. I'll use a dictionary comprehension to load them directly from the row. The format we need is a dictionary keyed by direction name, where the values are two tuples of required thing and destination, and the required thing is optional. I'll also use a simpler dictionary comprehension to load up the items. Now we can create our location object with the rest of the fields. Alright, we're all done. Now let's test out our load functions by putting some assertions in the main section of our file. We already have the state stored, so let's make sure that when we load it up, we get back an equivalent object. Good, it worked. Let's check a couple more examples to make sure. The test game file has some definitions for other game states, so we'll use them to make sure our storage code handles these different cases. It's really nice that we can just use equality on our entire game state to make sure this works. Okay, that's good for this lesson. We've created a module that deals with storage, and it's completely separate from our purely functional core game logic. Along the way, we learned the basics of SQLite and how to use it from Python. In this lesson, we'll be refactoring some imperative code that deals with data storage and SQLite to be more purely functional. You can find the code in storage1.py in your working files folder. Alright, so we've got some working storage code now. Let's do a bit of analysis on it. It's largely very imperative since we're interacting with the SQLite 3 module, which itself is imperative. Our functions are infected with the effects of the functions they call. But also notice that some of our functions are pure, specifically load location and serialize exits. Load location takes a row that's already been fetched from the database and converts it to a location object, with no side effects. Serialize exits takes one of our exits data structures and returns the JSON serialized format that we want to store in the database. It's important to try to look for opportunities to extract pure functions out of imperative ones. This is kind of a generalization of the functional core imperative shell concept. The separation between the core and the shell applies to more than the overall architecture of our program, like the separation of user interface from core logic. It can also be applied anywhere we need to do some imperative programming, such as in this storage layer. So let's look for some more code we can extract. One good way to do that is to look for the imperative bits and extract everything else into pure functions. The load state function will probably be the easiest. There are two imperative actions in that function, the query for locations and the query for the game state. We can separate these out with a bit of refactoring. Now we have smaller, easier to understand functions which are more reusable and easier to test. Only the 3-line load state function has any side effects. Let's make sure those functions still work. Okay, we can also apply a similar refactoring to the save state function. A lot of times when we refactor functions to make them simpler, we just grab bits of it based on some concern of the code, like saving a single location. We could do that here and extract a function that just handles saving a single location to the database. This seems like a decent refactoring and an improvement over the old code, but in some ways we've made our lives worse by increasing the number of side-effecting functions. This code is still reliant on the SQLite cursor's execute method to perform side effects, and testing it will be more difficult than testing a pure function. After thinking about it a little bit more, we can leave all the imperative code in the save state function and just extract out the pure bits. Unlike load state, though, the pure calculations in this function are dealing with the inputs to the effectful action rather than its return value. So we'll extract out the code that generates the parameters to pass along with the SQL statement. I'll call out to a serialized state function that returns the input parameters. The locations are a bit more complex. I'll extract a function that serializes the entire world at once and then iterate over it to run the SQL actions. We'll formulate serialized world by mapping a function that serializes a single location over the locations in the world. Serialized location is just like the code we originally had in the body of the for loop, except that it returns a tuple suitable for passing to the execute method. Again, we end up with a much smaller function that performs side effects, and a few other small functions that have pure behavior. And it still works. Okay, that's all for this lesson. We've successfully refactored our code to minimize the reach of side effects throughout our program. In this lesson, we'll extend our game's main loop with storage facilities. We previously implemented a storage subsystem, which you can find in the storage.py file in the working files folder. The main loop can be found in textui.py. We'll be working with both of those files in this lesson. By the end of this lesson, we'll learn a little bit about how to use functional abstractions to better factor our imperative code, as well as learn a couple more bits about SQLite. So we have our storage layer and we have a main loop. The feature we want to add is to make it so that the state of the game is reflected on disk after every turn. When the game is started, it should check for this saved state and continue from it if it exists. If you look at storage.py, there are three interesting functions we want to use: setup, save state, and load state. Setup initializes the schema of our database, save state writes our game state, and load state reads it back in. These are the functions we'll need to use from storage.py, but we'll also need to extend it a bit to manage some more bookkeeping. In TextUI, the interesting function we'll need to look at is main loop, as well as the code in the main section of our file. Let's start from the highest level and change our startup code to set up the storage. We'll work top down from there. We'll need a database connection in order to do anything, so let's just call a connectDB function to create one for us. We'll write this function soon. We'll also want to load the saved state, or if it's not there, use the predefined initial state. We'll call an initialize function to take care of this for us, passing the connection object. We'll say that initialize will return none when there was no saved data. In that case, we'll have to use the initial state. We can print out a little message to tell the user whether we're continuing. In order to keep this storage code separate from our game's main loop, we'll put it in storage.py, so I'll have to import those new functions. And finally, we'll have to use the calculated state to pass to main loop. Okay, so let's move over to storage.py. I'll implement the connectDB function that we just called. We'll just use a hard-coded path to a file where we'll keep the game state. So that's simple. Now for the initialize function. To initialize the state, we'll need to create the tables in our database. We have the setup function to do that. Then we need to load the game state object from the cursor, assuming the database already has data. So we have a couple of problems here. First, our setup function doesn't currently work if the schema has already been set up. It unconditionally tries to create the location and state tables even when they're already there. In addition to that, load state doesn't handle the case of an empty database. It raises an exception if there's no data in the state table. Fortunately, these are both pretty easy problems to fix. To solve the issue of creating the tables multiple times, we'll take advantage of a SQLite feature that allows us to only create a table if it doesn't exist. We just need to add the if not exists clause to the create table statements. The statement won't have any effect if the table already exists. Now when we call setup with an existing database, it won't blow up. To solve the problem with load state not handling empty databases, we just need to make a slight change to the way we're reading the data. Instead of blindly calling next on the result of the query to get the first row, we'll check if there are actually any rows before proceeding, and otherwise return none to represent no saved state. Now our load state function won't blow up when there's no data in the database yet. So now our definition of initialize should work. We should be able to run our game now, and it ought to create a new database file and print out creating new game. Let's test that out. Okay, so we see creating new game there. Of course, we haven't actually implemented the part that saves the game, but we should at least see that the database file exists, since the call to connect should create it. Great. Now let's get to implementing the saving. Since we want to constantly save the game state after every turn, we'll have to change our main loop function. We'll need a function that takes the state object and handles saving it to the database. Let's call it save and assume it's in the storage module for now. We can update our main loop function like this. Now let's define that save function in storage.py. Notice the call to the commit method. That's a new concept that I haven't mentioned yet. By default, all statements executed with the SQLite 3 module are run in a transaction, and they aren't really saved to disk unless you call the commit method on the connection object. So we do that in our save function, and now it's nicely abstracted from the main loop. We should now be able to run our game and see that the state is saved after each turn. Let's try it. Okay, so we see creating new game again because it couldn't load any data. I'll move east, which should save the game immediately. And to test that, I'll restart. Great, we're back where we left off outside on the street. So now we've got full functionality. We could wrap it up here. But what if we don't want to create a new connection every time we save the game? Our save function currently does that. It adds some overhead for every command the player runs in the game. I imagine that if we ran this over a network file system like NFS or SSHFS, it could be pretty noticeably slower. To optimize this, we'll need to share the connection object and pass it into the save function. Let's update the save function to do that. Since main loop calls save, that means main loop will also need to be updated to take the connection object. And walking all the way up, our main section will also have to be updated to pass the connection object in. So let's see if that works. Okay, it loaded our game. We should be able to take the rusty key and see that reflected on disk. Okay, we started up again and the rusty key is still in our inventory. All of this introduces a coupling problem though. We've been careful to keep all storage related code out of our core game loop, but now it's dealing with this connection object, which is specific to our storage backend. I'd prefer to keep those things strictly separated. For example, what if we wanted to support a different storage backend that didn't need a connection object, or maybe one that needed multiple different objects to deal with storage? We don't want to have to write different main loop functions to deal with the different storage backends. Ideally, it should only affect our startup code. With object-oriented programming, we'd probably define some abstract storage interface, and implementers would carry state along with it, and then implement it for a specific storage backend. This way, we can create the SQLite storage object in our startup code and then pass it into the game loop, which wouldn't need to know about the connection object. But that's a ton of boilerplate. Really, the only interface we need is some function that will save a passed-in game state. So why go to all the effort of creating a class and perhaps even an interface definition? We can just make our game loop function accept a function for saving the state. By using function closures, we can have the initialize code create the function so that the connection object is carried with it. Let's go to storage.py and do that. Then we'll just return it along with the state. Back in TextUI, our main loop function now only needs to accept the save function. Let's update the call in the startup code, and then the main loop function. We can get rid of that import now. So let's make sure this still works. Okay. So we're in the basement, and now I'll restart. Great, we're in the basement, we have the rusty key. Our save code worked. So now our core game loop has no specific knowledge of the storage backend being used, and we did it with much less boilerplate than the object-oriented solution. A lot of times when object-oriented programming calls for classes, they can be replaced with closures or partially applied functions, and you end up with much less code. Notice that while we're taking advantage of higher order functions here, they're not purely functional. Our save function decidedly relies on implicit side effects, and that's okay. We can use higher order functional abstractions in these cases and still gain a lot of benefit. Now, there are still cases where I'd use classes, especially when you end up with more complex interfaces that can't be represented by a single function. But I think it's better to keep things simpler until that complexity is really called for, and try to reformulate the code to use simpler functional abstractions where possible. So that's it. In this lesson, I demonstrated adding further functionality to a simple game loop. Pretty much everything we did was just imperative programming, but we used a functional programming technique, higher order functions, to carry state around and better factor our code. We also learned about how to manage schemas with SQLite using the if not exists clause, and also learned about committing database transactions. In this lesson, I'm going to lead us to the idea of first-class effects by exploring a way in which we can make our unit tests for imperative code much better. Our text adventure game currently has the following architecture. In core2.py, we have the functional core of simulation code. The functions in this module operate by returning new versions of game state and have no side effects. In storage.py, we have the imperative storage code. This is full of side effects, but it's pretty well contained. TextUI.py has our imperative shell with user interface and storage integration. We've made bits of it purely functional, but it's intrinsically all about having side effects, since it deals with user interaction and saving of the game state. We're going to be focusing on the imperative shell in TextUI.py. Let's look at its functions again. So main loop is an imperative function which repeatedly executes the step function and saves the game state. Step is another imperative function that runs a single interaction with the user. It takes the state, does some I/O, and returns a new state. Parse and dispatch are purely functional helper functions, which are already fine. Then we have the startup code in main. This is some imperative code that initializes the game and starts the main loop. Our goal is to completely rewrite main loop and step to be pure functions with no side effects. This is really the only core application logic we have that's still imperative, and we want to gain the benefits of purely functional code in it. The reason we want to make these functions pure is to make it easy to unit test our game's user interaction, and also make it more modular in case we want to implement different user interfaces or storage backends. Let's look at the test we currently have for the step function. This test currently uses the mock library to fake out the print and raw input functions. If we distill this test down to its essence, we want to verify two different things. First, that the result of calling step is what we expect, and second, that a series of specific side effects occurred. The mocking style of unit testing doesn't make this very clear. The mocking code is strewn all over the test, because we have to initialize some stuff before our call to step, and then run some assertions after it. Not only that, the test is also underspecified. It doesn't ensure the various side effects happen in the exact order we want them to happen in. It is possible to make those assertions with mock, but it's a lot more work and makes the test even less clear. Ideally, we'd have a way to specify this test that clearly and concisely describes what we want. I'm going to write some pseudocode demonstrating how I want to write this test. So first I'm going to declare the sequence of side effects that we want to occur. Here I'm saying that we expect the room's description to be printed, and it won't have any result. In other words, print returns none. Then we expect the user to be prompted for input. Notice that we're specifying that this side effect should result in the string move east, which simulates the user typing that into the prompt. Finally, we expect the string OK to be printed, and that's the end of our sequence. Now that we've defined our sequence, we want to actually run the step function and ensure that its result is what we expect, which is the game state where the player is in the street after having moved east from the house. While we run it, we want to make sure that the sequence of side effects occurs as expected. So that's it. This very clearly shows what we want to test, that we have a specific ordering of expected side effects. We provide simulated results for those side effects when appropriate, like for raw input, which returns a value entered by the user. For side effects that don't have a result, like print, we just have them result in none. This looks a lot better than the mock-based test. It allows us to specify even stronger assertions very clearly and concisely. So that's it for this lesson. I just wanted to give an idea of the kind of problem we're trying to solve. In the next lesson, we'll start to actually implement it and see how we can test our code with exactly this kind of specification. In this lesson, we'll update our text adventure game to use first-class effects so that our game loop is made purely functional. We'll be using the effect library to do this. I've described the idea of functional core imperative shell in other lessons. In order to facilitate the style of unit testing that we want, we're going to go further than that and make our shell purely functional as well. Of course, we still need some side effects somewhere in order for our program to actually do something useful when we run it. Instead of putting them in the shell, though, it's kind of like we're putting them in the background. First, let's look at our main loop and see what side effects we actually need. We'll start with the step function. Immediately, we see that we need to print things. That can be one type of effect. Second, we need to be able to prompt the user for input. This is an interesting side effect in that it's the only one we have that actually has a meaningful return value. Lastly, we need to be able to save the state to disk. Again, this is a side effect that has no return value. For the first two effects, we can take advantage of some predefined I/O objects defined in the effect library. The effect.io package has two classes defined: display, which represents the intent to display some text to the user, and prompt, which represents the intent to request input from the user. Note that I didn't describe these intents in terms of printing to standard out or reading from standard in. Since these objects are just transparent data with no behavior, we can abstract the specification of our effects from the way they're performed. So while we'll be using standard console-based I/O for now, they could feasibly be used for other types of interface, like a graphical user interface. Admittedly, though, they do imply a modal stream-based approach to user interaction. Our last effect, which is performed in the main loop function, is saving game state to disk. For that, we can take advantage of a simple convenience object in the effect library, which just wraps an imperative function to be used as a first-class effect. As a reminder, any object describing an effect is called an intent by convention. In the effect library, the effect class wraps intents and adds the ability to specify callbacks to be invoked after the side effect has been performed. Porting our code will be very simple since we're going to be taking advantage of effects do notation, which uses Python's generator syntax. By using that, we don't have to write callbacks by hand. So let's start with the step function. First, we add the do decorator to our function, which enables us to use the yield syntax to represent effects that should be performed. In the body, the first thing we'll do is replace our call to the print function. What we're doing here is first creating an intent to display that text, and then wrapping that intent in an effect object. Finally, we yield the effect to indicate that it should be performed before continuing the step function. This gives us a very imperative-looking way to describe our side effects while actually keeping it pure. I'm going to create a convenience function to make it easier to display bits of text in a less verbose way. Next, we need to replace this raw input call. We yield an effect of prompt here, and the yield expression will result in the actual user input that the user entered after the effect has been performed. Here we have another print function to replace. And finally, instead of using the return statement, in Python 2 we have to use the following syntax. If you're using Python 3, you can continue to use a plain return statement here and ignore the do return function. Now I'll quickly update the rest of the function. As you can see, very little changed between the normal imperative version of our step function and the purely functional version that uses the effect library. Basically, we used some predefined intents for printing and prompting, and used the do notation with yield expressions anytime we wanted to perform a side effect. Superficially, the code has changed very little, but it enables some interesting things later. We also need to update the main loop function. We add the do decorator again, just as we did for step, and here our step function now returns an effect. That's true of any function wrapped in the do decorator. So we need to wait for that effect to be performed by yielding it. The state that's passed to do return in the step function will be the result of this effect. After that, we need to save the state. We don't have any predefined intent objects specific to saving game state yet, so we can just use the func intent for now. The func intent takes a function to call along with any arguments. This allows wrapping it up in an effect to represent it purely. Alright, that's it. We've completely replaced our imperative shell with a purely functional shell by working with representations of side effects instead of performing them directly. But of course, there's still a little more work to do. Now our main loop and step functions return effect objects instead of immediately performing our game's effects. We need to update our startup code in the main section at the bottom of the file to actually perform those effects. We'll be doing that in the next lesson. In this lesson, we'll see how to perform first-class effects. We now have a purely functional game loop represented by the main loop function, which returns an effect object instead of starting the user interaction directly. We need to update our main script code to perform the effect object now. At the same time, I'll do a little bit of refactoring, since we should really be keeping the main script code to a minimum. I'll move most of the existing code into an imperative startup function. Now in our main section, we can call startup to get the save function and the starting game state. Now let's look at this call to main loop. Remember that this now returns an effect object. It won't actually start the main loop immediately. The effect represents the intent to run the main loop. So let's save that effect object in the mainf variable. In order to actually perform this effect, we use the sync perform function. The sync in that name stands for synchronous, which means this call will block until the effect completes, which in our case means the game is over. Note the dispatcher argument. If you recall, I said that the objects we use to represent effects don't have any behavior by themselves. They don't know how the effect should actually be performed. The dispatcher is what determines that. It's an object that looks up a performing function given an intent. We don't have to go into too much depth here since we're just using standard intents that already have performers provided by the effect library. The display and prompt intents have a dispatcher of performers that use standard console-based I/O. That is, they use the print and raw input functions to do the work, just like we were doing before. To enable performing the func intent and do notation, we need effects base dispatcher, which has performers defined for the most common basic intents. So we have these two dispatchers. Now we need to compose them together into a single dispatcher to pass to sync perform. For that, we use the composed dispatcher constructor. To compose some dispatchers, we just pass the dispatchers we want in a list to composed dispatcher. So that's it. While our startup code is made marginally more complex, the benefits we gain are pretty valuable. Let's run the game to make sure it works with our changes. Great, that's all I'm going to cover for this lesson. We've successfully ported our game to use first-class effects. In the next lesson, we'll update our unit test for this code to take advantage of this. If you'd like to do an exercise, take a look at the startup function. It's currently imperative, but you can use what you've learned in this lesson to also make it return an effect and be purely functional. In this lesson, we'll see how to test the first-class effects that make up our purely functional game loop. The code we'll be testing already exists in textui.py in your working files folder. As I discussed in the lesson about the desire for first-class effects, the two important things about any function with side effects are the result that it returns and the effects that it performs, in a specific order. The effect library provides a few very useful testing tools to help write unit tests against effectful code. The primary one is the perform sequence function, which simulates performing an effect while ensuring that exactly the expected effects are run in a specific order. It also returns the final result of that effect. This is exactly the tool we need to test those two crucial aspects of effectful functions. I'll be modifying the test.textui.py file in your working files folder. We're going to start by replacing the test step function, which currently uses mocks and doesn't really do a very good job. I'll just comment out the existing version. What this function really wants to test is the following. First, it wants to ensure that the room description is displayed. Then it should ensure that the user is prompted for a command. In this case, we want to simulate the user entering move east. Then it should ensure that the message OK is displayed. After running this sequence of side effects based on the initial state, it then needs to ensure that the final result of running the step function is a modified state, with the player's location changed to the street. So let's start writing our replacement for test step based on these goals. The first thing to know is that the perform sequence function takes a list of two tuples. First, an intent to expect, and second, a function to run to get the simulated result of that intent when it's performed. So to ensure that the room description is displayed, we write something like this. The first element of this tuple is a display object with the value we expect to be displayed in our step function. The second value is just a simple no-op function that we imported from the effect testing library. This is just a slightly more concise way to write a function that always returns none. Next, we expect the user to be prompted with a specific prompt. Here our function is a little more interesting to simulate the user typing move east, which becomes the result of that prompt effect. And finally, we expect OK to be printed. So that's the end of our expected effects. Now we'll call the step function to get the effect object that describes our procedure. Now we have all we need to use the perform sequence function. The first argument is the sequence we just defined, and the second argument is the effect we want to perform. It returns the result of that effect after simulating all the effects within the sequence. That result should be a game state object with the player in the street. Hopefully this test is a lot more clear than the mocking test we previously had. Let's run it and make sure it works. Great. Now let's write another test for an error case, when the user enters an invalid command. This function will look pretty similar to the last one. First we define a list of expected effects. In this case, we'll have the prompt effect result in an invalid command. And then we'll ensure that the right error message was printed. Again, we'll call the step function to get the effect. And then we'll call perform sequence to simulate that effect. The result we expect is just the same state that we passed in, since step returns the same state when it can't process a command. Let's make sure this one also passes. Great. Let's take another quick look at that step function. We have one more case that we haven't yet covered, handling of EOF error and keyboard interrupt exceptions. This is how we handle exiting the game when the user enters Ctrl-C or Ctrl-D on their keyboard. We'll write a test for quitting the game, and in it we'll simulate these inputs. We'll just repeat the same code for keyboard interrupt and EOF error to make sure that both exceptions are properly handled. To raise the exception, we'll take advantage of this raise function that's defined in the effect library. This is just a convenience function to work around the fact that Python doesn't allow you to put a raise statement in a lambda expression. When the exception is raised, we expect a friendly goodbye to be displayed. Again, we'll call step to get the effect object, and then we'll perform it with perform sequence. Since the step function calls sys.exit to quit the Python process, we need to handle the system exit exception here. And that's it. Let's make sure this also works. Great. So I just want to follow up with one more test case for the main loop function. We never wrote a mock-based test for that one. I want to show how easy it'll be to write it using the effect testing API. Let's consider the main loop function. It takes two arguments, a state-saving function and the initial state to start the game with. The state-saving function has implicit side effects, so the main loop function uses the func intent to wrap it up in an effect to represent it purely. We can test this by expecting that intent to be performed with a function we provide. That state-saving function is a bit interesting. It takes the state as an argument and has no result, so the only thing we care about is that it's called at the right time and with the right state. Since the implementation uses it effectfully wrapped in a func intent, we don't actually need to call it. Just ensure that it's performed with a func effect. So in our test, we just really need to represent it as a sentinel value that we don't expect to be called. Because of that, I'll make it raise an exception, just so we'll know if it is accidentally called. Now on to our expected effects. We start with some pretty familiar intents. I'll just copy them from test step. After that step is run, we have to ensure that the state-saving function is called. Here we specify a func that's equal to the one actually created in the code. It represents the state-saving function being called with the updated state, the one where the player is in the street. After that, the main loop repeats, so we expect another series of effects for running an iteration of the game loop. I'll simulate the user ending the game to stop it. This is just like what happens in test quit game, so I'll copy that sequence from there. I have to make sure that we're rendering the new location that we're in, and also simulate raising specifically the keyboard interrupt exception. So like our test quit game function, we want to make sure that system exit is raised, since we simulated the user ending the game in our sequence of effects. And that's it. Since the main loop function doesn't return any interesting value, we don't have any final assertion on the result. And it works. So notice how even though the end result of the main loop function is pretty useless, just a system exit being raised, we still have a very useful set of assertions about what it did. Specifically, notice how the data flows through the effects in our sequence. Because we simulated moving east, when we save the state, it's got the player in the street. And when the game is rendered, it also shows us in the street. Our sequence here makes that causality very clear, unlike in many mock-based tests. So that's enough for this lesson. We greatly improved our test suite for the step function and created a test for the main loop function, using the perform sequence function from effect. In this lesson, we'll see how to create custom intent objects for use with the effect library in the context of our text adventure. We'll be working with textui.py, storage.py, and testtextui.py from the working files folder. In textui.py, we have a main loop function which accepts a save function as an argument. It uses this to save the state. We did it this way so that the state saving interface in our application is generic. So while we currently only have a SQLite backend and we could just pass a connection object around, we wanted to make it so that the main loop didn't care about the details of storage. So instead we just pass in a function that abstracts away the details. There's an interesting pattern that effect enables, which is to invert the dependency relationship in cases like this. Instead of having a function accept a parameter to specify a dependency, we defer that to later, and instead use an effectful intent to represent that dependency. To do this, we take advantage of the separation between performers and intents in the effect library. We can have an intent called saveGame and supply the performer for that intent in our application's configuration. To support multiple backends, we can have multiple performers for that same intent class and choose whichever one we want when setting up our application. Anyway, let's get to the coding. First, I'll sketch out the changes to main loop. I can delete the save argument to main loop since we're no longer going to be using it. Then, instead of using a func intent to call that save function, I'll just use the saveGame intent. The nice thing is that this allows us to simplify the signature of our main loop function. It's back to only accepting a state object now. Now let's jump over to storage.py and implement the saveGame object. That's all it is, a simple class that has a single attribute and no methods. Most intents in the effect library work like this. I can also get rid of this save function we were defining and returning from the initialize function, since we no longer need it in the main loop. The last missing piece is a way to perform this intent in terms of our existing SQLite storage code. We have a save state function that already does most of the work we need. We just need a bit of a shim that we can give to the effect dispatcher that works according to its API. Most intent performers need to use the sync performer decorator, which allows them to just perform the effect and return a value normally. Performers usually take the dispatcher object and the intent to be performed. Usually the dispatcher can be ignored. In addition to that though, I'm making this function accept a SQLite connection object as its first parameter. We'll have to specify that by partially applying this function to the connection when setting up the dispatcher. Here we just call saveState with a cursor and the gameState object from the saveGame intent that we're given. And lastly, we commit the transaction. The last thing we'll do in storage.py is write a convenience function that sets up a dispatcher for saveGame objects that uses this performer we just wrote. This function will accept the connection object so it can be passed to the performer. The type dispatcher class allows you to create dispatchers that find a performer based on the type of the intent. It's the most common way to specify dispatchers with the effect library. You just give it a dictionary mapping intent types to their performers. We use the partial function to bind the connection object as the first argument to our perform saveGame SQLite function. That way, when the saveGame intent is performed, the connection is already available. So that's everything we need to do in storage.py. We just have a little bit more to do in textui.py to make our startup code use this dispatcher. We'll import the dispatcher setup function we just wrote so we can include it in our main dispatcher. Initialize no longer returns that save function, so I'll get rid of that. And then I'll set up that dispatcher. I'll change this startup function so it returns this dispatcher instead of the old save function. And then we just need to update the main section to use that new dispatcher. Alright, that's it. Let's make sure this code runs now. Okay, so I've moved east to the street, and when I restart, I should continue in the street. Great. It picked up our state from where we left off, so we know it works. There's one last thing I'd like to do before closing out this lesson. Our unit tests won't work with these changes. Let's go look at testtextui.py. The test for the main loop function will need to change. It's still passing in that save function. So I can delete our fake save function, and we can simplify the func intent to a saveGame instance. And finally, just delete the savefunc parameter to main loop. I'll just have to import saveGame now. And let's see if it works. Great. So in this lesson, we got rid of our use of the func intent to call a passed-in saveGame function and replaced it with a custom intent dedicated to saving our game state. This simplified both the application code and the test code by inverting the relationship of the dependency. We no longer needed to explicitly pass in the dependency to the main loop function. Instead, we encoded that dependency into its return value in the effect object. This kind of abstraction is often useful with the effect library. For example, if you're writing a client for a web API, you may ultimately implement things in terms of a write bytes to network intent, but abstracting that with, say, an HTTP request intent can clarify both the application code and the tests. Not only that, it gives your code an additional layer of modularity, since the intent can be implemented in different ways by different performers. As an exercise, consider adding another storage backend to the game. It should be possible to do this by providing another performer for the save game intent. Using the built-in pickle module would probably be the easiest, though it's worth noting that pickle has some big security problems and shouldn't be used in any real production code. Another possibility is to serialize the game state to JSON. In this lesson, I'll be introducing Flask, so we can later use it to give a web interface to our text adventure game. Flask is a tiny web framework compatible with Python 2 and 3. It's a fairly thin wrapper around two smaller libraries, Werkzeug and Jinja 2. Werkzeug provides basic abstractions for doing HTTP request and response processing, and Jinja 2 is a very simple and convenient templating system. On top of that, Flask adds a few convenience functions and a routing system for specifying which functions handle which URLs. While Django is probably a much more popular framework, a lot of people like Flask for its simplicity. It does very little by itself, though there's a pretty rich ecosystem of third-party extensions for integrating with various other systems. So let's dive into an example. I want to create a simple web app that allows the user to increment a number by submitting a form. The number will be stored as state on the server side, so different clients will see and be able to increment the same number. The first thing I'll do is create an HTML template for the app. First, we include some text that shows the current value of the counter. The double curly brace syntax is how you reference variables that should be provided by the application. Next, we need a form that allows incrementing the counter. This form has an input to allow the user to enter a number, and a submit button that will post a request to the increment endpoint when the user clicks the submit button. Okay, so that's the whole template. I'll save this file as counter.html inside of the templates subdirectory of my application, which is where Flask looks for templates by default. Next, I'll create a file called webcounter.py that has our application code for our web counter. The first thing I'll do is set up our counter state. I'll just do this as a global variable for now. And here's an increment counter function that adds to the global variable. In case it's not obvious, this is not a best practice. We'll talk about managing the state more effectively later. Now on to the Flask-specific stuff. We need to create a Flask object, which we'll use to declare our routes so we can handle requests to various URLs. The first route we'll add is the root. We want this to display the template with the current value of the counter. The render template function searches for the template in the templates subdirectory, and it accepts additional arguments for data to pass to the template. This is how we pass in the current value of the counter that the template uses. Next, I'll handle the increment route to handle the submission of the form defined in our template. We use the methods parameter to indicate we only want to accept post requests, as defined in our template. First, we get the number passed in with the form. Then we pass that number to the increment counter function that we already defined. And lastly, we return a redirect. This uses a kind of magical convenience function for finding the URL for a particular route. Instead of hard-coding the particular URL we want to redirect back to, we instead use URL4 to specify the route by name. This looks it up by the name of the function we used as the route handler, which we defined as root above. This is better than using URLs directly because it allows us to reorganize the URLs in our application without needing to change all the code. So that's all of the core code for our little web app. We just need to run the application to actually start a web server. The first thing I always do with Flask is enable this propagate exceptions configuration parameter. This makes it so that if one of our route handlers raises an exception, it gets printed to the console where we're running our app. Otherwise, Flask just swallows them, and it's very hard to debug what went wrong. To actually kick off the web server, we just call app.run. By default, this starts a web server on port 5000. Okay, so that should be the entirety of our little web counter application. We just need to run it in a terminal, and then we should be able to try it out. Flask helpfully prints out the URL that we can use to load the application. It's rendering the template and it shows the counter at 0. Let's make sure the counter actually works. Great, so our application appears to be working. That's all the code I'll cover, but I want to talk about some design considerations. There are two side effects on our code that are pretty much mandated by Flask. The obvious one is that our increment route handler modifies some state implicitly. Testing this will require us to deal with manual dependency injection or mocking. Even though our example is just a simple global variable for now, the same will apply to an application that uses a database. There's a more subtle issue in this code too, involving that request object. Notice that this is just a global variable, which we imported from Flask. It's not passed to our route handler. Our route handlers can't be pure functions if we have to implicitly rely on this external mutable state. If you're wondering how this works in the face of concurrent requests, Flask basically does some magic to keep the request local to a thread, so usually this isn't a problem. Of course, we can usually live with these infelicities in the API design and do our best to apply a functional core imperative shell design to our web applications. If you're curious about how you can write even your web routes in a pure functional way though, I'll be covering that in the next lesson. In this lesson, we'll be creating a tiny web micro framework that gives us a way to write purely functional route handlers in web applications. In the last lesson, we looked at a simple web application and discovered two things about the Flask framework that prevent us from writing pure functions to handle requests. First is that the request object is a magical global variable, and anytime we access it, we're relying on implicit mutable state. Second is that we have to perform our side effects implicitly in the route handlers. I'm going to write a little bit of code that solves both of these issues in Flask by making the following changes. Request objects will be passed as an argument to our route handlers, and handlers will be able to return effect objects which will be performed by the framework. In case you're not yet familiar with the Flask or effect libraries, I've covered them in other videos in this series. You should make sure you have the basics down before proceeding. Before I jump into developing the functional wrapper for Flask, I'll set the context by porting our web counter example to use the API we ultimately want. I've copied our webcounter.py file to a new one called fpwebcounter. So I want to provide a module named fpflask that has a functional Flask class. This will replace the Flask object in our application. I also want to get rid of the global request object and just have it passed into all of our routes, so I've removed that import. First, I'll switch our app object to use functional Flask. It'll work just like the Flask object. And then I'll add the request argument to all of our route handlers. Now I want to change our route handlers to use effect objects to represent their side effects. I'll use the do notation from the effect library and func intents to purely represent the calls to the side effecting functions. As a refresher, func is an intent that just wraps up an existing side effecting function to represent it purely. Before I update root, I'll need to add a getCounter function to encapsulate the retrieval of the mutable counter variable. The root handler will now get the value of the counter with effect. This will ultimately make it easier to test. And the increment handler will likewise need to indirect its call to increment counter through an effect. Since I want the functional Flask object to perform the effects for us, we need to provide it with an effect dispatcher. We're only using func intents right now, so we can just pass in the base dispatcher from the effect library. And I'll assume that the functional Flask object has the original Flask object as an attribute, so we can still access the configuration. Okay, so just a few changes and now our route handlers are pure functions. They only rely on explicit parameters and they don't have implicit side effects. They now return effect objects to represent their reading and writing to the global counter variable. So that's all for the example. Let's get to writing the fpflask framework now. So we're creating a functional Flask object that will be used just like Flask objects were. We'll create an underlying Flask object here to register routes with later. We also need to have a place to keep our route registration, so I'll create a list for that too. I'm providing a route method just like the original Flask API does. We're just going to stash the route handlers in a list along with the arguments passed so we can process them later. The reason we're not immediately registering the routes to the underlying Flask object is that we don't yet have the effect dispatcher, which we need since we want to be able to perform effect objects that are returned from these routes. So we'll get to that in the next method. And here's the first big difference in the API. Our run function will require the effect dispatcher to be passed to it. Since we have the dispatcher here, we can now process all those route handlers we stored away in the routes list. Here I'm just going through all our saved routes and using a method I haven't yet defined to register them. I'll implement that in a second. Finally, we run the underlying Flask application after having registered all the routes. So we need to implement this register route method that sets up our handlers. This is really where all the important differences from Flask are implemented. Here we can just use the route decorator from our underlying Flask object to declare our new wrapper. I'm also using the functools.wraps decorator to ensure that our wrapper function is dynamically renamed to have the same name as the route handler. So here's where the magic happens. This wrapper function is wrapping up the underlying route handler and will be called for every request. The first thing we're going to do is get the request object. The getCurrentObject method retrieves the plain request object from the magical global request. That way we can pass it around like a normal value. It may seem a bit scary to use an underscore prefixed method, but it is documented by Werkzeug, so it's safe to use. And here's where we'll pass in that request to the route handler, allowing it to avoid relying on the magical global request object. Finally, we'll process the result from our handler if it's an effect object. If it is, we'll just immediately perform it with our dispatcher and return the result. And if it's not, we'll just pass it back to Flask unchanged. So that's it. We now have a micro framework for doing pure functional web development. Let's see if our example works. Okay, so it's at least started up. And it's rendering the front page. Great, it seems to work. So now let me wrap up by going back to the code. Notice that this functional Flask object isn't functional itself. It does all sorts of mutation and side effects in order to implement this pure interface. The routes list is appended to as routes are registered, and of course we have a sync perform call to actually perform the effects that are returned from our routes. This is fine though. We always need some side effects somewhere, but we can push them further and further back in our systems so that more and more of our code can be written as pure functions. Essentially, the end goal of having more pure functions justifies the means of writing some implicitly side-effecting framework code. Making a pure FP web framework was pretty simple. We essentially just need to wrap our functions with a shim to handle the side effects for us. The main point I want to get across is that this applies in many cases. There are lots of frameworks and libraries in the Python ecosystem that require use of side effects in code that uses them, but we can isolate those side effects down into small utility libraries that handle them for us and give us a simpler API. I encourage you to apply this design where you can and make sure you share your code with the open source world. In this lesson, we're going to create a web interface to our text adventure game. We'll implement it entirely with pure functions using the effect library and the functional Flask wrapper we wrote earlier. To give you an idea of where we're going with this, I'm going to show you the final result of what we want our web app to look like. Here's what we want to implement. It's pretty similar to what we have in our text UI. We're displaying the name and description of the room, the list of the exits, the items on the ground, and our inventory. The main difference from the text UI is that instead of prompting the user for textual input, we simply have buttons representing the exits here. For example, if I click on the east exit, then the page is re-rendered and I'm now in the street instead of the house. On the street, I can see that the rusty key is on the ground, and I can click that button, and now it's in my inventory. So that's it. It's a pretty basic UI, but it will demonstrate a lot of what we learned. There's a lot of code in this lesson, so let's get to it. I'm going to start with the HTML template for the user interface. We're going to set up our application so the template has access to the entire game state. This makes it easy for us to get the location name and description and everything else. It's the only value we'll need access to. Now we'll deal with the exits list. Here I'm creating a form that's going to post to the move endpoint, which we can handle in the server-side application. This is a Jinja 2 for loop. They work almost identically to Python for loops, even supporting tuple destructuring, which we're using here. Any content inside the for block will be duplicated for each item in the thing we're iterating over. And this is our submit button. The server-side code will receive the value associated with the button being pressed, so it will know which exit to move through. Finally, we end the for loop with this end for statement. We'll do something very similar to the exits for the items in the location that we can pick up. Just like the exits, we loop over all the items and render a submit button. Lastly, we'll display the player's inventory, which is simpler since there are no actions associated with this, just a list of items we have. And that's it for the template. I've saved it in a file called game.html inside my templates subdirectory. Let's dive right into the application code. I'll save it in a file called webgame.py in the root of my project. I'll point out here that I've added some things to the storage module that we'll need for this lesson that I'm not going to go over in too much detail. There's a new load game intent in addition to the save game intent that we already had. This allows loading up the current game state in an effect. I also changed initialize to accept an optional initial game state to initialize the save file with. This will simplify our startup code. I'll show how later. These changes are in the copy of storage.py in working files for this chapter. As always, the first thing we do is create a functional Flask object so we can register route handlers. The first route we'll implement is the root. All this should do is load the current state of the game and render it with the template we defined. Here I'm using the load game intent that I defined in storage.py. It's going to load the game, and the result of it will be the state object. I'm attaching a callback which renders the game.html template, passing in the state object as a parameter. I could use do notation here, but I'll just return a plain effect using the on notation since it's shorter that way. The first action I'll handle is movement. There's a form that posts to the move endpoint, so we need to handle that. We pull out the exit name from the request.form dictionary. We'll also need the current state of the game so we can pass it to the core move function. Again, we use the load game intent for that. Since move can return none in the case of an error, like when we try to move through a locked door without the required key, I'll check before we save that new state. Then we'll always redirect back to the root page to show the player the new location. So that's it for the move handler. Taking items is very similar. Just like we did for the exit name, we get the item name from the form. And we call the take function to simulate taking the named item. The rest is pretty much identical. Feel free to refactor this code to reduce duplication as an exercise. All we have left to do is the startup code. We just need to initialize the database with the functions from storage.py, and then create an effect dispatcher that the functional Flask object can use to perform the effects we're using. Here I'm taking advantage of the new parameter to initialize that accepts the initial state of the game if there's not already some state saved to the database. Our dispatcher is the base dispatcher composed with our SQLite dispatcher from storage.py, which knows how to deal with save game and load game intents. The rest of the startup code is like any functional Flask startup code. And there we have it. Let's see if this works and I didn't make any typos. Well, it's running. Okay, it's working. Let's see if we can move around and make our way to the basement. Great, we did it. As we can see, Flask is a very simple and convenient web framework. We were able to create a fully functional UI for our simple text adventure game in an incredibly small amount of code. Since this is the last technical talk in the video series, I want to leave you with some good exercises to do if you want to keep working on this code. As I mentioned, these route handlers could be refactored a bit to reduce duplication in the state loading and saving and redirecting code at the end of each function. Also, these routes are pure functions and use effect objects to represent their side effects, so they should be testable using the techniques we went over in Chapter 8. Try to write some tests for the route handlers that use the perform sequence utility function. You'll need to simulate a request object. You could either create a simple inert object that has a form attribute, or you could figure out how to create a Verkzeug request object to use the real thing. Also, right now we don't do anything useful when there's an error in a move or take action, which is when they return none instead of returning a new state. Ideally, the web UI would show an error message of some sort. This is the conclusion of the video series on functional programming with Python. In this course, we've talked about some of the fundamentals of functional programming in Python and what it means to write pure functions. We also went over libraries like Toolz, Pyrsistent, Effect, and Hypothesis, which are all great libraries to go in your functional programming toolkit. While we were writing a simple text adventure game, we learned how to integrate third-party libraries like SQLite and Flask into our applications while isolating their side effects from the functional core of our code. So where should you go from here? I definitely encourage you to practice what you've learned either by extending the code we worked on in this course or working on your own projects. The game we wrote has a lot of opportunity for improvement. It's pretty boring right now, but adding new features should be pretty straightforward. It could also use a better user interface and maybe some more interesting puzzles. To introduce the concept you've learned into your own projects, I recommend doing it gradually. Start with some basic changes like avoiding spurious side effects. Make sure you at least are aware of which functions are pure and which have side effects, and perhaps mention those side effects in your docstrings. When you write new code, you can try to follow some of the guidelines you've learned to isolate your functional core from your imperative shell. From there, you can go on to using libraries like Toolz or Hypothesis, which are pretty easy to introduce into a project piecemeal. When you really want to go all in, think about libraries like Pyrsistent and Effect. So that's it. Thanks for sticking with me to the end. I hope you've learned something useful and that your code becomes more of a joy to work with.